Tonight, we're going to leave the solar system without leaving your chair. You are about to travel 4.24 light-years across space to Proxima Centauri b, the closest potentially Earth-sized planet we know. It was once hyped as the best nearby candidate for a second Earth. But James Webb just looked again with sharper eyes and deeper patience, and what it found is worse than anyone hoped. Before we get started, picture the scale of this mission: a space telescope the size of a tennis court, unfolded like an origami spacecraft, parked 1,000,000 miles from Earth at a gravitational balance point beyond the Moon. Designed to read the faintest whispers of alien atmospheres hiding in the glare of their stars. And then scientists turned that machine not on some distant galaxy, but on the very star system next door. For years, the story of Proxima b sounded almost comforting. An Earth-mass world, orbiting in the habitable zone, close enough that future generations might send a probe there within a human lifetime. The expectation was simple: if any nearby planet could hold on to oceans, air, and maybe life, it would be this one. The reality James Webb is sketching now feels very different. Proxima Centauri is not a gentle sun. It is a small red dwarf that flares violently, blasting its planets with intense ultraviolet and X-ray radiation. Proxima b races around it every 11 days at just 0.05 astronomical units, deep inside a region where the stellar wind is more like a storm. No one predicts that environment to be friendly. But there was still hope that a thick atmosphere, strong magnetic field, or deep oceans might shield the surface. So what happens when the most powerful space telescope ever built stares into that storm? At 424 light-years, Webb cannot take a postcard image of Proxima b. The planet is lost in the star's glare, too small and too close to resolve directly. Instead, the mission relies on tiny changes in starlight, on spectra, on the way different wavelengths are absorbed and re-emitted to reveal what kind of air, if any, surrounds that world. Here is where the journey becomes unsettling. Light from Proxima that is hitting Webb's mirrors tonight, left before some viewers were even born. That ancient signal passes the telescope's gold-plated boundary, is split into colours, and searched for the fingerprints of molecules that could mean oceans, clouds, or at least a stable sky. And in those fingerprints, scientists were hoping to see hints of survival. By the end of tonight, you are going to understand why what Webb didn't see in Proxima b's spectrum may be more terrifying than any obvious sign of danger. Because sometimes the absence of familiar gases, the silence where an atmosphere should be loud, is the clearest warning. Now, let's begin. So here is the paradox. Proxima b sits in what every textbook diagram calls the habitable zone, at just 0.05 astronomical units from its dim red star, where the energy from Proxima Centauri could, on paper, allow liquid water to pool on a rocky surface. A world in the right place, with the right orbit, around the closest star in our cosmic neighbourhood. And yet, the closer James Webb looks, the more that word habitable starts to sound dangerously misleading. Expectations were clear. If Proxima b carried a thick atmosphere, the transit spectrum during those brief crossings should show familiar fingerprints: water vapour, carbon dioxide, maybe methane, maybe even clouds muting and sculpting the starlight. Instead, Webb's first detailed observations delivered something that feels like a cosmic shrug, a nearly featureless transit spectrum, a flat line where scientists hope to see chemical structure, as if the planet either wears a cloak too uniform to decode, or no substantial cloak at all. That emptiness is only the beginning. While Webb watched, Proxima Centauri reminded everyone what kind of star it really is: an active red dwarf, a flare star. Sudden bursts of ultraviolet and X-ray energy, violent spikes in brightness, and evidence of a stellar wind far harsher than anything the solar wind delivers to Earth. No one expects a gentle environment at 0.05 AU from a star like this. No one predicts a quiet sky. The mission data show a star that repeatedly hammers any nearby atmosphere with enough power to erode it over billions of years. Before we get started on the details, it helps to frame the mystery. Earlier climate models painted Proxima b as a flexible world with options. Maybe a deep global ocean under a dense sky, maybe a tidally locked planet with a twilight ring of habitability, maybe even a robust magnetic field deflecting the worst of the stellar boundary storm. Webb's constraints slice through those optimistic scenarios. Many of the once promising combinations of surface pressure, temperature, and composition are now either strongly disfavored or effectively ruled out. So tonight, we're going to treat Proxima b as a test case for every red dwarf in the galaxy. Because if the closest example with all the advantages of proximity looks this hostile, what does that imply for the countless planets beyond our solar system orbiting similar stars? To keep this journey clear, there is a numbered promise. Together, we will walk through 7 major revelations from James Webb and related missions that, step by step, transform Proxima b from Earth 2.0 candidate into something far more precarious. By the end of tonight, you're going to understand not just what Webb saw and what it disturbingly failed to see, but what that silence means for the odds of life around the most common stars in the Milky Way. Because the central question is no longer, is Proxima b habitable? The real question is much sharper. Under this kind of relentless stellar assault, can any atmosphere survive long enough for life to begin? In the next segment, the first of those 7 revelations will push that question to the breaking point. That question becomes sharper when you remember which planet we're talking about. Proxima b is not just another data point in a catalogue. It is the world that, almost overnight, turned the entire exoplanet field toward our own cosmic backyard. In 2016, when scientists announced a planet around Proxima Centauri, the headlines were instant and relentless. Nearest star beyond the Sun, planet roughly Earth mass, orbiting right in the temperate zone where, on paper, liquid water could exist. Designed as a routine radial velocity survey of a faint red dwarf, the observing campaign suddenly had a celebrity on its hands. No one expects the closest exoplanet to also land in the habitable zone. No one predicts it will be almost exactly Earth-sized. That proximity does something to the imagination. Most exoplanets live as numbers on a screen, hundreds or thousands of light-years away, permanently out of reach for any realistic mission. Proxima is different. At just 4.24 light-years, it feels like the first stop on a future roadmap, the place a next-generation spacecraft might actually reach. When you look at a sky map of the solar neighborhood, Proxima b is not an abstract point. It is the nearest potential shore beyond our own world. Before we get started on what James Webb discovered, it helps to remember what people hoped for. Early models took the measured mass and orbit, plugged in a range of atmospheres and oceans, and many runs produced something striking. Global seas, under a dim red sun, thick clouds transporting heat from the day side to the night side, a dense, protective atmosphere buffering the stellar wind. Artists did not hesitate. Overnight, feeds filled with second Earth visuals, blue oceans, scattered continents, a crimson twilight sky. But underneath that optimism was a quieter warning. Proxima Centauri is a red dwarf flare star. It emits intense bursts of ultraviolet and X-ray radiation. Its magnetic field can whip the stellar wind into violent storms. Astronomers knew this, yet for years they lacked the tools to test what that meant for a planet parked only 0.05 astronomical units away, completing an orbit in just 11 days. Tonight, we're going to follow how that tension played out, expectation versus reality. A nearby, almost perfect Earth mass planet versus a host star that behaves more like a fusion-powered hazard light. By the end of tonight, you're going to understand why JWST pointing at Proxima b was not a routine observation. It was a very personal experiment. Now, let's begin. James Webb was sent to look beyond the solar system to read the faint fingerprints of alien atmospheres. When it turned toward Proxima, it was asking a question that goes straight to the heart of the mission. Can the nearest Earth-sized world actually be alive, or has its atmosphere already been stripped away? The first answers are not what anyone wanted to hear, and in the next section, that disappointment turns into something even more unsettling. A warning for almost every red dwarf, habitable zone, planet in the galaxy. When a telescope like James Webb starts hinting that our nearest Earth-sized neighbour might be more warning label than invitation, something interesting happens. If you're still here, listening to this solar system next door being slowly downgraded from hope to hazard, that says a lot about how your brain is wired. You are not just casually curious. You are the kind of person who lies awake thinking about what the wind feels like on a sky no human has seen, who wants to understand whether the planets around the nearest red dwarf are quiet, blue marbles, or blasted, airless rock. That kind of curiosity is rare, and it is exactly who this channel is built for. Before we get started with the really hard part of the story, take a second and look at the button right under this video. A quick like or a tap on subscribe is not just a formality. It is a way of saying, yes, this matters. Yes, these long arc questions about life, death, and atmosphere at the edge of habitability are worth time in the feed. Here is the undramatic, very real part. Algorithms are not scientists. They do not care about Proxima b or about how JWST disentangles starlight to search for a missing atmosphere. They care about signals. When a video gets engagement, it is treated as a signal that more people should see it. That is how more curious minds end up beyond the headline of Earth 2.0 discovered and into the actual physics of radiation, magnetic fields, and atmospheric escape. Pattern interrupt for a moment. Think about the last viral space headline that crossed your screen. Habitable world found. Signs of life? No one predicts those thumbnails will walk through the caveats, the error bars, the way a red dwarf's flare can erase an ocean over billions of years. But that is the gap this community tries to close, taking the same dramatic missions and telescopes and refusing to leave out the part where the data fights back. By the end of tonight, you're going to understand why Proxima b went from closest potentially habitable planet to cautionary tale for almost every red dwarf habitable zone in the galaxy. That is the level of detail this channel aims for. Not just wonder, but mechanism. Not just the dream of a second Earth, but the hard question of whether such a world can survive its own star. So, if that is the journey you want more of, join the mission now, and then let the video run. The focus stays on the story. The rest of this episode is going to stay with the data, the spectra, and the models, and follow them wherever they lead. Now that we're on the same page, let's rewind and see how we got to the point where James Webb is delivering bad news about our nearest neighbour, and what earlier generations of scientists thought Proxima b might be before the new observations arrived. To understand what Webb is doing to Proxima b, you have to go back to the moment humanity first learned to read the invisible. Before we get started on red dwarfs and stripped atmospheres, rewind to two small, rugged spacecraft, leaving the inner solar system in 1977. Voyager 1 and 2 are not sleek observatories, they are metal boxes with spinning tape recorders, 8-track memory, and cameras that would look primitive next to a phone. Designed for a 5-year mission to study Jupiter and Saturn. They are still talking to Earth nearly 50 years later, far beyond Pluto, feeling their way toward interstellar space. No one expects that. No one predicts that these spacecraft, with transmitters weaker than a household light bulb, will end up discovering the true boundary of the solar system. Yet as they push outward, their particle detectors and magnetometers watch the solar wind fade, listen as the interstellar medium grows louder, and finally cross the heliopause into a region where the sun's influence truly ends. The boundary is farther than scientists calculated. The shape is not the neat sphere in the textbooks, but a distorted, dynamic bubble being carved by a galactic headwind. The magnetic field twists in directions absolutely no one anticipates. Voyager shows that the edge of the solar system is not a line. It is a complex, violent transition zone that theory alone never captured. That is the pattern. Crude, brave instruments go out first, and the universe responds by breaking our models. Then the tools evolve, from flyby cameras snapping volcanoes on Io and fractured ice on Europa, to ultraviolet detectors mapping the solar wind, to precision infrared spectrometers that never leave Earth's neighborhood, but can dissect the light of distant planets. Tonight, we're going to treat Webb as the heir to that entire lineage. Where Voyager sampled charged particles with metal foils and gas counters, JWST measures tiny dips in starlight, photon by photon, and teases out the fingerprints of molecules in an atmosphere that cannot be seen directly. Water vapor, carbon dioxide, methane, even the absence of those gases, all encoded in a spectrum across a few microns of infrared. By the end of tonight, you're going to understand why this is not a new question, just a new arena. For decades, every mission has been aimed at the same core mystery. What else is out there? And could it host life? From Titan's thick nitrogen sky to Europa's hidden ocean, from the heliopause to the void beyond, each spacecraft has pushed the search for habitable environments a little farther from home. Now, let's begin the next step. JWST is the first observatory powerful enough to seriously probe the atmospheres of small, rocky exoplanets around nearby stars. That makes Proxima Centauri b not just a convenient target, but a symbolic one, the closest, potentially habitable world, orbiting a star whose radiation and wind may be rewriting our expectations all over again. To understand why Proxima Centauri b's story just took a darker turn, you have to meet the star that controls its fate. Proxima Centauri is not a gentle sun. It is small, dim, and crimson, and that combination makes it far more dangerous than it looks. Proxima is a red dwarf, the runt class of stars that dominate our galaxy. It has about an eighth of the Sun's mass and is so cool that most of its light comes out in deep red and infrared, glowing more like a banked ember than a blazing furnace. It lurks as the third member of the Alpha Centauri system, a faint gravitational companion to the brighter sun-like pair, Alpha Centauri A and B, orbiting them from far out in the darkness. Before we get started on Webb's bad news, it helps to realize how common this kind of star really is. Red dwarfs are not rare curiosities, they are the rule. By number, They are the majority of stars in the Milky Way, perhaps 3 out of every 4. Tonight, we're going to treat Proxima not as an odd neighbour, but as a template. What happens in this tiny system is a preview of what billions of planetary systems might be facing all across the galaxy. Expectation. A small, cool star should be calm. Reality. Proxima is a flare star. It erupts, frequently, violently. Its magnetic fields twist and snap, launching bursts of ultraviolet and X-ray radiation that can make the star brighten by factors of several in minutes. In 2016, one super flare briefly made Proxima visible to the naked eye from dark skies, a sudden spike in power from a star that usually hides in the background. Those outbursts are not gentle space weather. They are more like repeated nuclear detonations on a stellar scale, washing nearby planets in high-energy photons and charged particles. The solar wind from a star like this can be dense and erratic, pushing hard against any planetary atmosphere, probing for weaknesses at the boundary between space and air. Now, let's begin to connect that to habitability. Because Proxima is so cool and faint, its habitable zone huddles extremely close in. Proxima b orbits at only about 0.05 astronomical units, with an 11-day year, tucked far inside Mercury's orbit if it were in our solar system. To receive enough warmth for liquid water, it has to cling to the star's side. That means every flare, every surge of radiation, every gust of stellar wind slams almost directly into any atmosphere it might have. By the end of tonight, you're going to understand why that proximity is such a problem and why no one predicts a simple, Earth-like environment there anymore. One of JWST's quiet powers is to watch stars like Proxima in the infrared, catching subtle changes in brightness and heat as flares rise and fall. Scientists use those data to reconstruct just how hostile this system really is and to test whether a world so close to a star this volatile can survive for billions of years. No one expects what Webb is about to reveal next about Proxima b's chances. To understand what Webb is really seeing, you have to understand the strange year of Proxima b. This is not a gentle Earth-style orbit with 4 seasons and a leisurely trip around the Sun. This is a tight, relentless loop around an ember. Proxima b circles its red dwarf once every 11.2 Earth days, not months, days. At a distance of about 0.05 astronomical units, it orbits roughly 20 times closer to its star than Earth does to the Sun. If you dropped Earth into that orbit around our own star, the oceans would not just boil, the crust would glow. The only reason Proxima b is not a literal lava world is that Proxima Centauri is so much dimmer and cooler than the Sun. That extreme proximity is both the headline and the trap. In terms of raw energy, Proxima b receives something surprisingly familiar, a total flux, not wildly different from what Earth gets. This is why, when the planet was first discovered in 2016 through subtle wobbles in Proxima's motion, scientists placed it squarely in the star's nominal habitable zone. On paper, it checked the first box, a world where liquid water could exist on the surface. Tonight, we're going to see why that first impression was dangerously incomplete. Before we get started on atmospheres and escape, there is a more basic problem: mass and size. From radial velocity, the mission teams measure how much Proxima Centauri rocks back and forth under the planet's gravity. That gives a minimum mass of about 1.3 Earth masses, but the radius is unknown. No transit has been conclusively detected, so there is no direct measurement of how big Proxima b actually is. Without size, density is a mystery. It could be a compact, iron-rich world, a more Earth-like mix of rock and metal, or something with significant water. Each option reacts very differently to Proxima's radiation and wind. Then there is the way it spins. At 0 till 5 AU, tidal forces are brutal. Over millions of years, they act like a cosmic brake, draining rotational energy until the planet almost certainly falls into tidal locking. One hemisphere locked in perpetual day, staring into a red sun. The other in endless night, frozen, starlit, never seeing dawn. Between them a narrow twilight band where, in early models, some hoped liquid water might persist. By the end of tonight, you're going to understand why that picture now looks far more fragile. Being in the habitable zone turns out to be a geometric statement, not a guarantee. It says nothing about atmosphere, magnetism, or whether a planet can survive the boundary conditions set by its star. No one predicts what happens when JWST looks for heat patterns on such a world and instead finds almost nothing. Because if Proxima b really is tidally locked, really is Earth-like in mass, and really is sitting in that razor-thin band of temperate light, then the next question is brutal. How much of it is still there to be warmed at all? For a while, the answer many scientists preferred was comforting. A planet can be brutal up close to its star and still hide a gentle face. Proxima b in the early models was that hidden gentleness. The first climate simulations took a tidally locked world, parked it in Proxima Centauri's dim red light, and gave it one crucial gift: a thick, resilient atmosphere. With enough air, the wind could haul heat from the blazing dayside into the frozen dark, smoothing the extremes. Not a uniform paradise, but something stranger and more enticing. A permanent ring of twilight circling the terminator, where temperatures hovered in the liquid water range. Imagine that boundary. One hemisphere locked under an eternal red noon, the other under a black, star-spattered midnight, and between them a band of perpetual sunset, where oceans could breathe and clouds could form. Tonight, we're going to stand in that ring for a moment, because this is the version of Proxima b that drove so much of the excitement. In those models, dense air and fast circulation created jets, storms, and a global climate engine that refused to let one side burn while the other froze. Add water, and the picture became even more seductive. Some runs placed global oceans on Proxima b, turning it into a dark sapphire world with thick cloud decks reflecting the worst of Proxima's tantrums. Others allowed for deep basins, inland seas, glinting patches of liquid that shifted with long-term climate cycles. Clouds on the day side could block ultraviolet flares, while water vapor and carbon dioxide trapped just enough heat on the night side to keep it from locking into permanent airless ice. From there, the leap to life did not feel outrageous. By the end of tonight, you're going to understand how optimistic the community once was. In the rosiest scenarios, future space telescopes would tease out spectral fingerprints from that atmosphere. Oxygen and ozone hinting at photosynthesis. Methane in stubborn imbalance with carbon dioxide, maybe even subtle combinations that screamed chemistry out of equilibrium. Not proof of biology, but a loud, persistent whisper. And because Proxima b is only a little more than 4 light years away, proximity poured fuel on the dream. This was not some unreachable planet on the far side of the galaxy. This was the poster child for interstellar missions. Laser sail concepts like Breakthrough Starshot sketched out gram-scale spacecraft pushed by ground-based beams to 20% the speed of light, racing across the void in a human lifetime. No one expects cameras flying past a real exoplanet so soon. No one predicts that a single nearby world will suddenly make that sound plausible. Pattern interrupt. In those early years, the question was which flavor of habitable Proxima b nature had chosen, not whether the word habitable belonged there at all. Thick atmosphere or thinner one, global ocean or patchwork seas, strong biosignature gases or only faint hints. Now, let's begin to turn. Because the new constraints from JWST do not gently adjust those hopeful models. They take entire families of them and move them off the table, forcing a confrontation with a much harsher version of our nearest planetary neighbour. So, how do you even judge those models when the planet itself is invisible? Proxima b is far too small and far too close to its dim red star to separate cleanly, even with the most powerful space telescope ever launched. At 424 light-years, it's a single unresolved point. The trick is that the planet still leaves fingerprints on the light from Proxima Centauri. Tonight, we're going to follow that light. When a planet crosses in front of its star, it shaves off a tiny fraction of the star's brightness. That is the transit method. A rocky world like Proxima b might block less than 1% of the light, but with sensitive instruments, that dip becomes a measurable signal. And if that world has an atmosphere, the signal is not the same at every color. Here is where transit spectroscopy comes in. As starlight filters through a planet's atmosphere, atoms and molecules grab very specific wavelengths. Water vapor, carbon dioxide, methane, they all carve out their own narrow notches in the spectrum, measure the star's light before, during, and after a transit, and the comparison acts like a chemical barcode scanner for entire planets. But there is a problem. For Proxima b, even the transit itself is uncertain. Some observations hint at shallow dips, others see nothing. No one predicts that studying the nearest potentially habitable exoplanet would start with a debate over whether it even crosses its star from our viewpoint. So scientists are forced into a different kind of mission design. Stack many observations, use multiple techniques, and hunt for signals that sit right at the edge of detectability. This is where JWST's infrared spectrometers become crucial. Instruments like NIRSpec and NIRIS can spread Proxima's light out into thousands of wavelength channels and measure changes of a few dozen parts per million. In the infrared, molecules that matter for habitability speak loudly. Carbon dioxide leaves broad, sculpted features. Water vapor etches deep valleys. Even if Proxima b's transit is marginal, repeated passes let scientists average down the noise and search for those signatures. By the end of tonight, you're going to understand why the absence of those features can be just as powerful as their presence. A flat spectrum with no bumps where an atmosphere should imprint is not a failure. It is a verdict. It says, no thick hydrogen envelope, no steamy global ocean shrouded in vapor, no dense Earth-like air, rich in CO2 at the pressures we hoped. Before we get started on the grim details, hold on to that idea. Around a violent red dwarf whose wind and radiation can strip worlds, a non-detection is not empty. It is the boundary line where optimistic atmospheres end and harsher realities begin, and that is exactly where JWST's new view of Proxima b lands. So when the first spectra came in, the story everyone wanted was simple. A nearby world with a clear, breathing sky. What arrived instead was a much quieter message. The atmosphere, if it existed at all, refused to show itself. Now, let's begin with the tools that tried to coax that message out. Ground-based observatories using high-resolution spectrographs watched Proxima's faint light and searched for the subtle fingerprints of molecules being tugged along by the planet's orbit. Space telescopes from Hubble to Spitzer tried to tease out tiny color changes as Proxima b moved in front of or around its star. The pattern was frustrating. No obvious oxygen bands, no strong water vapor features, no thick Neptune-like shroud, just noise limits and silence. This wasn't just a Proxima problem. As the exoplanet catalogue exploded, scientists pointed their instruments at dozens of small, close-in worlds hugging their parent stars. Expectations were bold. Hot mini-Neptunes with swollen, steamy envelopes, super-Earths with rich, exotic skies, planets whose spectra would light up with deep absorption lines from water, methane, carbon dioxide. Reality pushed back. Again and again, instead of forests of features, the spectra came back almost flat. Flat is not exciting to look at, but it is incredibly revealing. A flat line can mean a wafer-thin atmosphere hugging the surface, so tenuous that even the best instruments cannot see its imprint. Or it can mean a world smothered in high-altitude clouds and hazes, a uniform grey blanket that smooths out every feature, from water to carbon-bearing molecules, into an almost featureless continuum. For many of these close-in planets, those two options became the leading suspects. Tonight, we're going to connect that larger pattern back to Proxima b. Orbiting at just 0.05 astronomical units, circling its red dwarf every 11 days, Proxima b sits in a region where stellar wind and high-energy radiation are relentless. Models showed that over billions of years, this onslaught could erode a thick atmosphere, blow away oceans, and leave a bare, rocky core. Yet there was still room for hope. With the right magnetic field, with enough initial gas and water, perhaps a substantial atmosphere could survive, altered but not erased. Here is where upper limits become the quiet heroes of the story. When a telescope fails to see a signal, that absence is not meaningless. It lets scientists say with quantifiable confidence that any atmosphere must be thinner than some threshold, or that certain molecules like water vapor or CO2 cannot be present above a given abundance. For Proxima b, early non-detections began to carve out whole regions of parameter space where an Earth-thick, clear atmosphere simply could not hide. By the end of tonight, you're going to understand why that mattered so much when JWST entered the scene. With its sensitivity, if Proxima b carried a robust, Earth-like sky, at least a hint should rise above the noise. So what does it mean when the most powerful space telescope yet stares at our nearest exoplanet neighbour and the line stays almost perfectly flat? To answer that, you have to follow the gaze of the James Webb Space Telescope to where it lives. Not out by Jupiter. Not drifting through the outer solar system. Webb sits 1,000,000 miles from Earth, balanced on a gravitational knife edge called Sun, Earth L2, with the Sun, Earth, and Moon all on one side and deep space on the other. That position is not about distance, it is about silence. On the hot side, a 5-layer sunshield the size of a tennis court blocks almost all heat and light from the Sun and our planet. On the cold side, the spacecraft radiates its own warmth away until its mirrors and instruments chill to just a few tens of degrees above absolute zero. Ultra-stable, ultra-cold. Exactly the conditions scientists need to see the faintest heat from planets beyond our solar system. Now, let's begin with what Webb actually sees. Unlike Hubble, which focused heavily on visible and ultraviolet light, JWST is tuned to the infrared. That is where many of the most important atmospheric molecules leave their fingerprints. water vapor, carbon dioxide, methane, ozone and carbon monoxide. Each one absorbs light at very specific wavelengths, carving tiny notches into a planet's spectrum that transits straight through the glare of the star. During a transit, when a planet like Proxima b passes in front of its star, NIR Spec and NIRISS watch the starlight filter through any air that might cling to that world. They break the light into thousands of colors, searching for those notches. Later, when the planet slips behind the star in a secondary eclipse, MIRI can look for the planet's own thermal glow, disappearing and reappearing, a direct probe of its temperature and possible atmosphere. On paper, it sounds straightforward. In practice, the signal from an atmosphere on a small rocky planet is vanishingly small, so the observing strategy leans on patience and repetition. Multiple transits, multiple eclipses, the same measurements taken again and again, then stacked together to push down the noise until only persistent features remain. Those combined spectra are then compared against models: a thick, Earth-like atmosphere, a Venus-style hothouse, a thin Mars-like envelope, or a bare rock with almost no air at all. Tonight, we're going to see why that modelling becomes especially powerful for a system only 4.24 light-years away. Proxima is close. Its planet orbits every 11 days. That means transits repeat quickly, giving Webb many chances to catch the planet in silhouette and in eclipse. And here is the boundary where expectation meets dread. If any current telescope could give a clear yes or no on whether Proxima b holds on to a substantial atmosphere, it would be JWST. No one expects a perfect map of alien weather. No one predicts cloud patterns or continents, but a strong, obvious, atmospheric signal. That should stand out. So when those instruments stare and the spectra come back nearly featureless, the silence is not just disappointing, it is a warning. Because if Webb cannot hear Proxima b breathing, the next question is brutal. What, exactly, has been stripping that world bare? So what did Webb actually hear when it listened for that breath? Almost nothing. When scientists pulled Proxima Centauri's new spectra out of the glare of its star, they went hunting for familiar fingerprints, deep, broad troughs where carbon dioxide absorbs infrared light, subtle wiggles from water vapor, maybe even hints of methane or other volatiles that would betray a thick, complex atmosphere. For a nearby world in the habitable zone of its star, that is the expectation. But the data come back flat, eerily flat. Now, let's begin by clearing up a common misconception. A near featureless spectrum does not mean Proxima b is literally airless, a bare rock, with nothing above the surface. Transit spectroscopy is a blunt tool at 4.24 light-years. If the atmosphere is very thin or dominated by molecules that do not imprint strongly at Webb's wavelengths, or hidden beneath high, uniform clouds that smear out features, the spectrum can look almost empty. The planet could still have air, but that air is hiding at the edge of what this mission can see. Before we get started on the implications, compare this to what many models predicted before JWST ever opened its mirrors. Simulations of Proxima b under optimistic conditions, an Earth-like inventory of water, a Venus-like load of carbon dioxide, and a magnetic field to help fight the stellar wind, suggested that even with Proxima's violence, a substantial atmosphere might survive. Not pristine, not gentle, but thick enough that Webb should at least glimpse broad CO2 bands, the way it does when it looks at hot, volatile-rich planets much farther from our solar system. Expectation, a world that still holds on, leaving clear chemical scars in the starlight. Reality, no strong, obvious CO2, no towering absorption, from nitrogen-rich air, just constraints, upper limits, and silence where a signal should be. That silence pushes the models in a darker direction. If a thick, volatile-rich envelope was still wrapped around Proxima b, the most powerful space telescope ever launched should have seen some hint of it. The lack of such features tilts the scales toward harsher scenarios. An atmosphere that has been eroded over billions of years by relentless ultraviolet and X-ray radiation, or a planet that never managed to build a deep reservoir of gases before the stellar wind started tearing at it. Designed to test whether nearby red dwarf planets can endure, this mission is instead showing how fragile that endurance might be. Tonight, we're going to watch that optimism unravel. By the end of tonight, you're going to understand why a flat spectrum is not just a technical result, but a profound downgrade. Proxima b is probably not the lush, cloud-wrapped world of early artwork. It may be a far more bare and exposed planet, clinging to whatever thin veil of gas it has left, while its star keeps trying to finish the job. To understand what James Webb is really telling you about Proxima b, you have to watch the slowest kind of violence in the universe, a star peeling a world like an onion, not in minutes, in billions of years. Now, let's begin. Atmospheric escape sounds gentle, almost poetic. It is not. High-energy ultraviolet and X-ray photons slam into the upper atmosphere, dump energy into the gas, and heat it until the fastest particles reach escape velocity. Once those atoms cross the planet's gravitational boundary, they are gone, drifting into space, never to fall back. Earth lives with this process too. Our upper atmosphere boils off a thin trickle of hydrogen and helium all the time. But the mission profile here is forgiving. At 1 astronomical unit, the Sun's high-energy output is weaker, and Earth's strong magnetic field funnels most charged particles toward the poles, turning solar storms into auroras instead of global sandblasting. Over 4.5 billion years, the planet has lost only a tiny fraction of its air. Proxima b's situation is the contrast pair to that calm story. Expectation? A temperate world in the habitable zone. Reality, a planet parked 20 times closer to its small star than Earth is to the Sun, completing an orbit in just 11 days. In that tight configuration, models suggest it absorbs tens to hundreds of times more extreme UV and X-ray radiation than Earth. The same physical process that gently shaves our atmosphere becomes a blowtorch. When that radiation hits, the upper layers swell and expand, turning the atmosphere into a puffed-up target. High above the surface, where gravity's grip is weakest, atoms and molecules acquire enough kinetic energy to outrun escape velocity. Hydrogen goes first, then lighter molecules like water vapor fragments, and over long spans, even heavier gases can be dragged along in a hydrodynamic wind flowing away from the planet. But photons are only half the story. Proxima Centauri launches a continuous stellar wind, a stream of charged particles that can be far denser and more violent than the solar wind bathing our own system. If Proxima b is tidally locked, with one face permanently staring into that red glare, its interior may cool faster, weakening the dynamo that powers a magnetic field. No shield, plus a stronger wind, means direct atmospheric erosion. Particles are sputtered off the top of the atmosphere like grains from a sand-blasted rock. Before we get started on exotic chemistry or life, this is the first survival test. By the end of tonight, you're going to understand why JWST's flat spectrum does not look like a missing signal anymore. It looks like the expected outcome of a long asymmetric war between star and planet. a mission of erosion that began the day Proxima b formed. And the worst part is what that war implies for every other habitable world around red dwarfs, including one target that absolutely no one anticipates. Tonight, we're going to watch Proxima Centauri lose its temper in real time. Because once JWST and its companions started staring, the quiet red ember next door turned into something closer to a strobe light. The original picture is simple. A small red dwarf, a close-in planet, some flares here and there, but nothing that Proxima b could not ride out over billions of years. No one expects the violence to be worse than Earth's worst solar storms by orders of magnitude. No one predicts that when the multi-wavelength campaigns switch on, Proxima will immediately start misbehaving. To really understand what is happening, scientists do not just point one telescope and hope for the best. They stack a whole arsenal. JWST watches in the infrared, sensitive to subtle changes in heat and brightness. X-ray observatories like Chandra and XMM Newton track the highest energy blasts. UV satellites, including Hubble and dedicated solar-style monitors, measure the wavelengths that shred atmospheres. Together, they turn Proxima into a continuous experiment, catching the star in the act instead of reconstructing its anger from a few scattered events. The result is brutal. Some superflares spike Proxima's brightness by factors of 10 or more in the UV and X-ray bands, lasting from a few minutes to over an hour. For Proxima b, sitting only about 0.05 astronomical units away, that is like standing a few meters from a welding torch, while someone keeps turning the power knob past maximum. By the end of tonight, you're going to understand that even Earth's famed Carrington event looks modest compared to what Proxima can throw repeatedly at a planet stuck in its tight orbit. Here is the pattern interrupt. Earlier flare catalogues made Proxima look dangerous but manageable, a volatile neighbour that calms down often enough for atmospheres to recover. With JWST's sensitive infrared monitoring and nearly continuous high-energy coverage, the flare rate jumps. Events once thought rare show up weekly. Smaller flares fill in the gaps between the monsters, the quiet baseline that models used as a safe period. It almost disappears. Every one of those outbursts has consequences. High-energy photons slam into the upper layers of any remaining atmosphere, heating and expanding it so that stellar wind can peel it away more easily. Repeated hits erode ozone-like shields, letting UV light reach the surface unfiltered. Temporary sterilization waves sweep across the dayside, baking away fragile organic chemistry before complex biology has a chance to stabilize. It is not one apocalyptic blast. It is a long, grinding attrition campaign. So this becomes the second major downgrade. First, JWST hints that Proxima b no longer carries the thick, protective atmosphere that habitability models once favored. Now, the star itself reveals an even harsher reality, a relentless flare engine, more extreme and more frequent than almost anyone anticipated. And if the closest red dwarf is this hostile, the next question is obvious. What does that say about all the other habitable zones around red dwarfs across our galaxy? So if Proxima b no longer carries that thick, protective shroud, what does the actual surface feel like under a star this violent? Tonight, we're going to step onto that world in imagination just long enough to understand why JWST's bad news feels so personal. Picture standing on the dayside. The sky is dim, not bright blue, but a heavy copper-red gloom, because a cool red dwarf simply does not flood space with light the way the sun does. Shadows are long, colours are muted. Then, without warning, Proxima flares. The star that was a dull ember becomes a welding arc. A white-blue flash tears across the sky, so intense that the red glow vanishes for a moment in a sheet of actinic glare. From that surface, there is no safety in sunglasses or sunscreen. Without a thick atmosphere or a strong magnetic field, the planet's boundary with space is naked. High-energy ultraviolet X-rays and charged particles crash straight down, not filtered, not deflected, just delivered. On Earth, even extreme solar storms are filtered through our ozone and our magnetic field, turning into auroras. Here, the same energy slams into rock, ice, and whatever unlucky molecules sit exposed at the top of the regolith. Scientists can quantify it, but the human experience would be simple. Unshielded life is almost impossible. DNA would shatter faster than it could repair. Cell membranes would rupture. Complex molecules that biology depends on would be carved apart by radiation faster than chemistry could rebuild them. A surface microbe that might survive a rare Earth flare as an inconvenience would, on Proxima b, face that onslaught as a routine part of the daily or weekly weather. Maybe, you might argue, life hides. Beneath rock, under an ocean, beneath kilometers of ice. That is the next hope. But repeated flares do not just hit the ground, they rewire the atmosphere above it. Each blast can strip away ozone, the very layer that blocks the harshest UV. The ozone reforms slowly. The flares come fast. By the end of tonight, you're going to understand why that rhythm matters. Each event opens a temporary window where killing light penetrates deeper than before. Over thousands, then millions of years, those windows stack. Radiation seeps farther into the ocean, it reaches deeper rock. The safe zone for potential ecosystems shrinks, crushed downward by the star's rage. On Earth, the worst solar storms on record are historical curiosities. 1859, 1989, rare spikes in an otherwise gentle solar wind. On Proxima b, events of that scale may be Tuesday. The romantic picture of a calm twilight world, bathed in soft red light, dissolves. In its place stands a planet living under a cosmic strobe, every flare a brutal reminder that not every habitable zone in the galaxy is truly habitable. Now, let's begin to ask what that means for all the other red suns lighting up our neighborhood. So, the flares are brutal. The radiation is relentless. But to know what Proxima b is really going through, scientists need one more thing. It's heat. How the planet glows, not in visible light, but in infrared. That's where James Webb quietly becomes a climate detective. Before we get started, picture something simple. A world locked in a tight 11-day orbit, always showing nearly the same face to its star, like the moon does to Earth. One hemisphere, in perpetual day, blasted by red light and charged particles. The other in endless night staring out into interstellar space beyond the solar system. The question is not just how hot Proxima b is, the question is where that heat goes. This is where phase curves enter the mission. As Proxima b circles its star, the total light, star plus the planet's faint thermal glow, changes by a tiny amount. By tracking those changes over an orbit, telescopes like JWST can reconstruct how bright the day side is, how dim the night side is, and how quickly temperatures shift from one limb to the other. It is like watching a rotating ember and inferring where the hottest coals lie, even if the ember itself can never be resolved. For a planet wrapped in a thick, stable atmosphere, the expectation is clear. Winds grab heat from the day side and haul it toward the night, smoothing extremes. The temperature contrast shrinks. Day is hot but not hellish, night is cold but not absolute zero, and the thermal phase curve looks gentle, with a broad peak and a soft decline. That is the kind of profile scientists once hoped to see from Proxima b, a sign that air, clouds, maybe even oceans were sharing the energy. But the emerging picture is harsher. Models tuned to JWST's early thermal measurements combined with previous constraints point toward a relatively sharp day-night contrast. The day side wants to be blazing, the night side wants to be frozen. The phase curve that best matches the data looks more like a bare rock, with limited heat redistribution than a world wrapped in a thick, protective sky. By the end of tonight, you're going to understand why that is so unsettling. No one expects a single dataset to deliver a verdict. The signal is faint, the star is noisy, and every assumption about composition or clouds can nudge the inferred temperatures. But the trend is uncomfortable. A thin or absent atmosphere here lines up a little too well with the missing spectral fingerprints and the savage stellar wind. Three independent lines now converge: spectra that show no obvious air, flares that can strip it away, and heat patterns that refuse to smooth out. No one predicts that all three would point in the same grim direction. And absolutely no one anticipates what happens if the next observation, even more sensitive than this one, confirms that Proxima b's night side is nearly as dead as airless space itself. So far, the story has been simple. A world that looked promising, then a telescope that keeps telling you the air is gone. But what if the real mistake isn't thinking Proxima b lost an Earth-like atmosphere, it's assuming it ever had one at all? This is the pattern break. Tonight, we're going to flip the script on what habitable zone even means around a star like Proxima Centauri. On paper, Proxima b sits at a distance where liquid water could exist. In reality, that single number hides a very different kind of solar system physics. Around red dwarfs, planets do not have to form the way Earth did. They can grow in a drier disk, with fewer ices drifting inward and under a young star that blasts them with high-energy radiation from day one. Before we get started, think about how planets form around a calmer star like the Sun. Volatile material, water, carbon dioxide, nitrogen, can condense, migrate, and build thick atmospheres over time. Now put that same process next to a flare star that throws out superflares and violent stellar wind for hundreds of millions of years. No one expects a gentle nursery. The early boundary between can keep an atmosphere and get stripped to the core, shifts inward, then inward again, until worlds in the habitable zone are sitting in a long-term sandblaster. In that environment, Proxima b might never have been an ocean world. It could be more like a scaled-up Mercury, dense, iron-rich, and almost airless from birth. Mercury, in our own system, orbits close to the Sun with a huge metal core and only a wisp of exosphere. Now, imagine that template pushed outward around a cooler red dwarf, but still locked under intense X-ray and ultraviolet bombardment. By the end of tonight, you're going to understand that Earth-like orbit does not guarantee Earth-like outcome. JWST's constraints do not choose a single nightmare. They are compatible with several. Proxima b could be a stripped former ocean world where early seas boiled and bled into space under relentless radiation. It could be a baked-out desert with a thin, heavy cloak of residual gases hugging hot rock. Or it could be that primordial bare rock, a world that never accreted much volatile material, never built a thick sky, never had a serious chance to stabilize liquid water at the surface. This is the deeper reframing. Instead of a paradise lost, Proxima b might represent something harsher, a warning that many habitable zone planets around red dwarfs were never truly habitable to begin with. The label tracks distance from the star, not protection from its fury. No one predicts that a single nearby planet could force scientists to question billions of catalogued, potentially habitable worlds. And absolutely no one anticipates what happens when the same logic is applied to entire populations of planets around the most common stars in the galaxy. So when James Webb turns its mirrors toward Proxima b and finds almost nothing, that silence hits harder than any dramatic signal. The most powerful infrared observatory in space stares at our closest, potentially habitable neighbor, and the spectrum comes back nearly flat, like a voice cut off mid-sentence. Now, let's begin with what scientists were hoping to see. In the infrared, every common atmospheric molecule leaves a fingerprint. Water vapor carves out broad, deep bands. Carbon dioxide slices the spectrum at very specific wavelengths. Methane paints sharp notches. In the most optimistic scenarios, there might even be hints of ozone or other oxygen-bearing species, fragile traces of a world with active chemistry. Tonight, we're going to follow those missing fingerprints. JWST doesn't just look for obvious towering signals. Its instruments are sensitive enough to weigh the absence of features and turn that into hard limits. If Proxima b were wrapped in a thick, Venus-style carbon dioxide blanket, the spectrum would be unmistakable. CO2 has strong absorption bands in the mid-infrared. A massive CO2 atmosphere would hammer those wavelengths, producing deep, repeated dips that even a noisy, flare-ridden star could not fully hide. Those dips are not there. By the end of tonight, you're going to understand why that is more than a technical detail. It means very thick CO2-dominated atmospheres, the kind that could stabilize temperatures and shield a surface from wild stellar swings, are strongly disfavored. The boundary between plausible and implausible climates shifts. What remains on the table are thinner envelopes, patchy atmospheres, or exotic mixtures that avoid the usual signatures. The same story plays out with methane. Around temperate planets, methane can accumulate from geology or biology, building a clear infrared signal. Here, JWST can place upper limits that cut down those possibilities. No one expects methane alone to guarantee life, but its weakness on Proxima b makes many of the more Earth-like climate models much harder to sustain over billions of years. Water vapor is the harshest blow. If Proxima b had a dense, moist atmosphere with active weather, even modest humidity would etch recognizable water bands. Instead, Webb's data allow only low levels or atmospheres so thin that water never has the chance to cycle. That points toward a dry world, or one where water is locked away in ice, rock, or a buried ocean, hidden from space and from spectroscopy alike. Chemically, Proxima b is whispering, not shouting. Its infrared quiet is itself a loud statement about the environment. No one predicts that a near neighbor would look this muted, this constrained, and absolutely no one anticipates how that silence will reshape the next generation of missions that dare to search for a true Earth among the planets of red dwarf stars. That silence from Proxima b tempts you to imagine a quiet refuge, a brutal beginning perhaps, followed by a long, gentle middle age where oceans could settle and life could adapt. That is how the story works for many stars in our own solar neighborhood. Massive flares, violent winds, intense ultraviolet radiation. Young stars throw tantrums. Over time they spin down, their magnetic fields weaken, and the fireworks fade. The Sun followed that arc. It was more active in its youth, then gradually calmed, giving Earth billions of relatively stable years to build continents, atmospheres, and complex biospheres. By the end of tonight, you're going to understand why Proxima Centauri refuses to follow that comforting script. For low-mass red dwarfs, the expectation used to be similar: a nasty adolescence, then a long, steady adulthood. But prediction met observation, and observation won. New models that track stellar rotation, convection, and magnetic dynamos, combined with decades of X-ray and UV monitoring from space telescopes, show that stars like Proxima can stay magnetically saturated for astonishing fractions of their lifetimes. In that regime, the outer atmosphere of the star boils with activity. Flares are not rare events, they are the background. The stellar wind is not a breeze, it is a storm. Proxima's surface field stays strong, the corona stays hot, and the high-energy output barely declines on timescales where sun-like stars would already be settling down. No one expects a star this small to stay this angry for this long, but that is what the data keep insisting. Proxima Centauri is not a young star. Age estimates put it at several billion years old, comparable to or older than the Sun. Yet it still erupts with super flares that can increase its brightness in ultraviolet and X-rays by factors of tens to hundreds in minutes. When James Webb stares at this system, it has to navigate around that constant flicker, building light curves that show a star that never truly rests. That has brutal implications for Proxima b. Orbiting at just 1205 astronomical units, the planet lives deep inside this magnetic storm. Continuous high-energy bombardment over giga-year timescales does more than give you bad space weather. It strips atmospheres molecule by molecule. It drives chemical reactions that break apart water, blow hydrogen into space, and leave oxidized, desiccated surfaces behind. Life does not just need liquid water and a temperate orbit. It needs time. Long, calm intervals where an atmosphere can thicken instead of erode, where a surface can cool instead of bake, where complex ecosystems can survive not just one flare, but millions of them. For Proxima b, that temporal window keeps shrinking. Every model that extends Proxima's active phase pushes the hypothetical golden age of habitability closer to zero width. Tonight, we're going to confront a harsher possibility: that there was never a quiet epoch at all. No serene ocean world in the past, only a planet locked under a sky that has been hostile from almost the first moment it formed. And if Proxima b never had a peaceful era, the next question is even more unsettling. What does that say about all the other red dwarf worlds we hoped might be safe harbors just beyond our own solar system's boundary? So if Proxima b might have lived under a hostile sky from the very beginning, the next step is uncomfortable but necessary. You look for a control case. Another red dwarf system loaded with Earth-sized planets that has already been pushed to the limit. That system exists. It's called TRAPPIST-1. TRAPPIST-1 is only about 40 light-years away, an ultra-cool dwarf star with 7 known planets, all roughly Earth-sized, all packed into orbits tighter than Mercury's. When it was first announced, it sounded like science fiction made real. Multiple worlds in the habitable zone, multiple chances for oceans, clouds, maybe even biospheres. Tonight, we're going to use that promise and what followed as a warning label for Proxima b. The original hope is simple: cool star, low luminosity, planets close in but in the right temperature range. No one expects all 7 to be paradises, but it seems reasonable that at least a few could hold thick, volatile-rich atmospheres. Water vapor, carbon dioxide, maybe something more exotic. By the end of tonight, you're going to understand why that early optimism has been quietly dismantled, one spectrum at a time. Hubble, Spitzer, ground-based telescopes, and now the James Webb Space Telescope have stared at these worlds as they cross their star. During each transit, a thin shell of starlight filters through any atmosphere and imprints spectral fingerprints of gases. Prediction versus observation could not be clearer. Models said strong features, deep absorption bands, obvious signs of air. The data? For several TRAPPIST-1 planets, the spectra are flat or eerily muted, as if the signal has been scraped clean. Flat spectra can mean two things. Either the atmospheres are so cloud-choked that features are hidden, or the atmospheres are thin to the point of near non-existence. That's where the pattern interrupt arrives. When scientists fold in TRAPPIST-1's stellar violence, the cloudy paradise option starts to look less likely. TRAPPIST-1 is quiet invisible light, a dim ember in space, but in high-energy ultraviolet and X-rays, it can be ferocious. It flares. Often, superflares, powerful bursts, and a relentless stellar wind slam those close-in planets. Over billions of years, that high-energy radiation can break molecules, heat the upper atmosphere, and drive gas beyond escape velocity. The result is atmospheric erosion on a system-wide scale, a slow excavation that can leave multiple habitable-zone planets as bare, desiccated rocks. Now, let's begin drawing the parallel no one wanted. Proxima Centauri is even more active than TRAPPIST-1. Its flares are stronger. Proxima b orbits closer in, whipped by intense UV, X-rays, and a brutal stellar wind, all inside a compact solar system boundary where magnetic shielding is hard to maintain. If TRAPPIST-1's gentler environment may have stripped several planets, what chance does Proxima b realistically have? The implication is stark. Proxima b is not an isolated disappointment. It is one gravestone in a growing TRAPPIST-1-style cemetery. Across the galaxy, red dwarf habitable zones may be littered with the corpses of once hopeful worlds. The next question is whether any of them ever escape that fate, or whether JWST is starting to show that the most common stars in the universe may be the least forgiving hosts for life. That cemetery image forces a deeper question. If so many promising worlds around red dwarfs end up as cosmic gravestones, was the promise ever real? Or was the entire idea of a red dwarf habitable zone a mirage from the beginning? Before we get started, rewind to the classic definition. In every astronomy textbook, the habitable zone is that neat ring around a star where, in principle, liquid water can exist on a planet's surface. Not too hot, not too cold. Given a suitable atmosphere, you could have oceans, clouds, maybe even continents. It sounds clean. It sounds objective. It sounds like a simple geometric problem. Draw a band at the right distance and count the worlds inside. But hidden inside that phrase, given a suitable atmosphere, is a huge assumption. It assumes the atmosphere is there. It assumes the atmosphere can survive for billions of years. Around a quiet star like the Sun, that shortcut often works. Around a flare-active red dwarf like Proxima Centauri, it can fail spectacularly. Proxima b is the perfect illustration. On paper, its orbit at about 0.05 astronomical units drops it squarely into Proxima's habitable zone. The same is true for several of the TRAPPIST-1 planets. Designed on the whiteboard, these systems look like compact, efficient engines for making temperate worlds. But when JWST and other spacecraft actually probe them, the picture shifts. Flares, extreme ultraviolet radiation and relentless stellar wind turn that just right zone into a demolition range for atmospheres. So, being in the habitable zone of a red dwarf often means living in something closer to a blast furnace, with the thermostat set to maybe survivable only in simplified models. No one predicts that a planet can sit that close to a star, that violent and emerge unscathed, not once the numbers for flare energy and particle flux are on the table. By the end of tonight, you're going to understand why orbital distance alone is starting to look like the least important part of the story. This is where JWST's grim hints become transformative. Tonight, we're going to see that astronomers are being pushed to rebuild the very idea of habitability. It is no longer enough to say a planet is the right distance from its star. Now, habitability has to fold in stellar activity levels, the strength and geometry of planetary magnetic fields, the ability of an atmosphere to repair itself after repeated blasts, and the long-term balance between atmospheric loss and replenishment. The sobering implication is hard to ignore. The most common stars in the galaxy, the countless red dwarfs that dominate our local region of space, may offer the least truly habitable real estate. If that is true, then the boundary between likely life and permanent sterility moves outward, away from these tiny, violent suns and back toward rarer, quieter stars like our own, and absolutely no one anticipates how much that could reshape the search strategies for the next generation of missions. Now, let's begin asking what that means for our nearest targets, and whether any red dwarf world can ever really beat the odds. So now, stepping back from all the details, the pattern around Proxima b is hard to ignore. At the start, this planet was the dream case, Earth mass, in the habitable zone right next door in cosmic terms. Now, every new pass with James Webb is turning that dream into a warning sign painted across our nearest stellar neighbor. First, there is what Webb does not see. Those missing strong atmospheric signals during transits are the silence that speaks loudest. A thick, cloudy, temperate atmosphere should leave obvious fingerprints in the spectrum. Instead, scientists are scraping the noise, looking for hints and finding almost nothing. Taken alone, that absence could be a trick of geometry or clouds or instrument limits. But it does not stand alone, because wrapped around that silence is extreme flare activity. Proxima's surface erupts with UV and X-ray violence, blasting its planets with energy far beyond what Earth receives. Webb catches that restless star in action, and the implication is clear. Any atmosphere on Proxima b has spent billions of years standing in front of a blowtorch. A single flare might be survivable. A lifetime of them is different. Then there are the large day, night temperature contrasts. Instead of a gently redistributed warmth, the thermal pattern looks sharp and uneven, as if the planet cannot move heat efficiently from the star-facing side to the night hemisphere. That is exactly what would be expected from a thin atmosphere, or no substantial air at all. On its own, it could be explained away by exotic circulation. Combined with the missing spectral lines, it becomes part of a story. The chemistry is quiet too. No obvious water vapor bands, no confident signs of carbon dioxide or methane. Chemical silence where a living, breathing world should at least whisper. Again, a single missing molecule would not be decisive, but an entire forest of expected features failing to show up, that is different. Layered on top of all this, Webb's view of Proxima's long-lived stellar violence and the eerie parallels with the TRAPPIST-1 system push the conclusion further. This is not one unlucky planet. This looks like a pattern around small active red dwarfs. The classic habitable zone concept, drawn as a neat ring where liquid water can exist, starts to look compromised when the star's wind, flares, and fields are factored in. Distance alone is not protection. Tonight, We're going to treat Proxima b less as a failed hope and more as a crucial data point. By the end of tonight, you're going to understand how this nearby world is teaching mission planners where to look next in the galaxy and where caution is warranted. We set out wanting Webb to confirm a nearby living world. Instead, it is teaching what can quietly kill worlds that look perfect on paper. No one expects a single planet to rewrite the search for life, but when our closest candidate starts to look air-poor, flare-burned, and chemically mute, the next question becomes unavoidable. If Proxima b is a warning, what does it say about the thousands of red dwarf planets still waiting in the dark? If Proxima b is a warning, the next shock is how many worlds that warning might apply to, because Proxima is not a cosmic oddball. It is the rule. Now, let's begin with a quiet, unsettling fact. In the Milky Way, red dwarfs, the cool, dim M-dwarfs, are not a minority class of stars. They are the majority. Roughly 70 to 75% of all the stars in our galaxy are small, red, and faint, more like Proxima than like the Sun. For every familiar yellow Sun-type star, there are several Proximas humming along in the dark. That imbalance changes the search for life. If most stars are red dwarfs, then most of the real estate for planets is anchored to these tiny, turbulent suns. And that is exactly what planet hunters have discovered. When spacecraft like Kepler and TESS stare at the sky, the easiest planets to see are the ones circling small stars. A planet passing in front of a red dwarf blocks a larger fraction of its light. The signal is deeper. The wobble in the star's motion is stronger. The boundary between detection and noise shifts in our favor, so catalogues fill up with M-dwarf worlds, temperate super-Earths, compact solar systems with several planets packed closer than Mercury. Some sit in the habitable zone where, on paper, liquid water could exist. Before we get started talking about how grim Proxima looks, remember that for more than a decade, this was the optimistic headline. The galaxy might be teeming with small rocky planets in the right temperature range, around stars that can burn for trillions of years, long lifetimes, stable light output, abundant planets, designed for habitability, or so it seemed. Tonight, we're going to confront the contrast between that expectation and what Proxima is actually showing. Because when JWST stares at this nearby red dwarf system and finds signs of atmospheric loss, brutal radiation, and a relentless stellar wind, it is not just diagnosing one unlucky planet. It is stress testing an entire strategy. Prediction versus observation. The prediction said, common stars plus common planets equals vast chances for life. The observation from Proxima hints at something harsher. If flares, X-rays and charged particles routinely erode atmospheres in the habitable zones of red dwarfs, then many of those promising planets may be airless, desiccated rocks. The inventory of truly habitable worlds shrinks, not by a little, but potentially by orders of magnitude. By the end of tonight, you're going to understand why what happens at Proxima is not a local weather report. It is a statistical clue about the entire galactic landscape. No one predicts a single red dwarf could sway estimates of life in the Milky Way. Yet if Proxima b is typical instead of tragic, then every flare star system we discover beyond it might be whispering the same hard truth. The next step is to ask, is there any way for a world in that firing line to survive? Survival is the next question, not comfort, not oceans and sunsets, just the bare minimum. Can chemistry stay organized long enough to call it life under a star that wants to erase it? On Earth, the early guess would be no. Yet life has already embarrassed that intuition. Microbes cling to the cooling ponds of nuclear reactors, quietly feeding in a radiation field that would shred human DNA in seconds. Others live kilometers underground, sealed in rock, surviving on the faint chemical energy from radioactive decay and water-rock reactions. By the end of tonight, you're going to understand that when it comes to radiation, biology cheats in ways no one expects. So when Proxima's flares slam Proxima b with X-rays and ultraviolet light, scientists do not immediately cross out the word life. They start asking where it could hide. One refugee is underground. A few meters of rock or ice can blunt even a brutal stellar wind, turning lethal space weather into a distant rumble. If Proxima b ever held water, that shielding could extend to subsurface aquifers, salty pockets locked beneath a frozen crust, or fractures where liquid seeps through warmer rock. Another possibility is a deep ocean, if one ever existed. High-energy radiation dies out quickly in water. A planet-wide ocean tens or hundreds of meters deep could turn the surface into a sacrificial skin, while microbial communities rest safe on the seafloor, feeding on hydrothermal vents, metal-rich sediments, or slow chemical gradients. That picture is closer to Europa than Earth, a world where the sky is an enemy and all the real action happens in the dark. Now, let's begin to connect that to what James Webb actually sees. Those hidden niches are wonderful for survival. They are terrible for detection. Microbes sealed beneath rock or buried under ice leak almost nothing into a planet's atmosphere. No forests to pump oxygen, no global plankton blooms to sculpt reflectance. Just tiny, local chemical imbalances, easily drowned out by Proxima's violent chemistry. So when JWST stares across 4.24 light-years and finds no convincing atmospheric features on Proxima b, the signal is not no life anywhere. It is no large, loud biosphere near the surface. The boundary between those two is crucial. Tonight, we're going to feel that gap, because it is exactly where many early hopes for Earth 2.0 were living. No one predicts a rich blue, cloud-laced world hiding an entire biosphere underground. Absolutely no one anticipates that as the default outcome of a flare star system. Survival in Proxima's glare is not impossible in principle, but it would be a life of hiding, not flourishing. A planet of cryptic microbes clinging to shadows, while the star above writes a very different story into space. The next question is brutal. If Proxima b looks like this, what does that say about all the other red dwarf habitable zones scattered through the galaxy? So is that the end of the story? A dead, airless rock locked to a hostile red dwarf? Not quite. There is one narrow category of atmosphere that could still be hiding in the glare, slipping through James Webb's current reach. Now, let's begin with the most conservative option. A thin, high molecular weight blanket. Not a thick, Earth-like sky, but a meager envelope dominated by heavy gases such as CO2, or even denser species like sulfur dioxide or argon. These molecules hug the surface more tightly, produce shallower spectral features, and if the atmosphere is only a few % of Earth's pressure, their signature can drown in Proxima's noise. At 4.24 light-years with a small planet in front of a tiny star, that is exactly the kind of signal JWST struggles to pull out. Tonight, we're going to imagine Proxima b as a world where the atmosphere never vanished completely, but was crushed and distilled down to its heaviest remnants. In that regime, transmission spectroscopy becomes brutal. The scale height is small, the absorbing layer is thin, and the contrast between planet and star is microscopic. No one expects an easy detection there, even with the most powerful space telescope in the solar system's history. But there is an even stranger possibility. Instead of a classic CO2 cloak, Proxima b could carry an exotic mix: metal vapors from a superheated crust, photochemical hazes spawned by intense UV, or volcanic gases like sulfur compounds and chlorine species that do not carve big, broad fingerprints in the infrared. Think of a planet where relentless flares crack molecules apart faster than they can settle, where the atmosphere is a shifting fog of reaction products that ride the stellar wind and recombine in unexpected ways. By the end of tonight, you're going to understand why that kind of sky is a nightmare to characterize. These edge-case atmospheres do not rescue the surface. A thin, heavy shell has limited greenhouse power. It traps some heat, but not enough to smooth out the brutal day-night contrast on a tidally locked world. Exotic hazes can block a fraction of ultraviolet light, yet they are no match for Proxima's X-ray barrages and charged particle storms. Radiation still slams into the ground. The boundary between airless and barely aired is not a boundary between hostile and friendly. It is a boundary between different flavors of harsh. So even in the most optimistic of these scenarios, Proxima b does not snap back into the promising column. It moves from stripped rock to marginal world, from vacuum to a tenuous veil of gas that offers poor protection and fragile stability. No one predicts thriving oceans under that sky. At best, there are pockets of relative safety, transient windows when conditions are less lethal rather than truly benign. Yet for scientists, these possibilities are gold. Constraining how thin, how heavy, and how exotic Proxima b's air can be forces models of atmospheric escape, volcanic outgassing, and stellar interaction to agree with real data from a real planet. It sharpens our tools before the next mission stares at another faint world beyond our solar system and sees only a hint of absorption lines buried in noise. Because here is the unsettling part. If Proxima b really sits in this grey zone, it might be the template for thousands of red dwarf habitable planets. And the next clue to that pattern may come from something JWST was never designed to see directly, but might already be revealing in the background of its data. So, is it possible that everyone is just reading Proxima b's spectrum the wrong way? That somewhere, in those thin, jagged lines, a living world is hiding behind bad calibration and a noisy star? Before we get started, it helps to remember what this mission is trying to do. JWST is pushing exoplanet spectroscopy right to the boundary of what is physically possible. Proxima b is small, close to its star, and 4.24 light-years away. The signal from any atmosphere is tiny. The noise from the star, the instrument, and interstellar space is huge. Scientists are not just taking a picture, they are subtracting a star from a star plus a planet and hoping the difference is real. That's where stellar contamination comes crashing in. Proxima Centauri is not a calm, uniform disk of light. It's a restless red dwarf with star spots cooler than their surroundings and faculae that are hotter. As the star rotates and flares, those regions imprint their own spectral fingerprints. Dark spots can mimic the dimming caused by molecules in a planetary atmosphere. Bright faculae can wash out or distort absorption lines. The result is a spectrum where stellar weather can masquerade as planetary climate. Tonight, we're going to sit right inside that uncertainty. Different teams build different models of Proxima's spotted surface, different maps of its faculae. Different assumptions about how the stellar wind and magnetic fields evolve over time feed the same JWST data through these models, and the answers do not line up perfectly. One group might say there could be a very thin atmosphere but nothing like Earth's. Another might argue for a bare rock, with only trace gases sputtering off the surface. No one predicts a lush, Titan-thick shroud from these spectra. By the end of tonight, you're going to understand why, despite all this debate, the big picture has barely moved. Independent analyses using different pipelines, different contamination corrections, and even slightly different subsets of the data keep converging on the same conclusion. There is no strong evidence for a dense, Earth-like atmosphere on Proxima b, not the kind that can easily hide oceans. Not the kind that shrugs off billions of years of X-ray and ultraviolet punishment. Here's the pattern interrupt. If JWST were simply missing a thick, life-friendly atmosphere, the easiest mistake would be to confuse atmospheric lines with stellar ones. But that mistake would usually go in the opposite direction. Contaminated spectra tend to create false positives, not erase a huge, robust signal. When the best the data can offer is maybe a wisp, it's hard to argue there is secretly a deep, protective sky. Now, let's begin to look ahead. Future observations, more transits and better stellar models can still sharpen the verdict, maybe nudge Proxima b from probably bare to marginally cushioned. But given what has already been discovered about its violent star and muted spectrum, it is very unlikely that JWST has simply overlooked a blue, cloud-wrapped world waiting just beyond the glare. To feel what JWST is really saying about Proxima b, you have to imagine running the mission yourself. Tonight, we're going to design the observing campaign that would either reveal a breathing atmosphere or prove that space has already stripped it away. Start with the clock. Proxima b orbits its star once every 11 Earth days, hugging that dim red dwarf at only about 0.005 astronomical units. Each time it slips in front of Proxima Centauri, the transit lasts only a couple of hours. The planet is small, the star is small, and the signal is tiny. So the schedule becomes ruthless. Scientists book transit after transit, secondary eclipse after secondary eclipse, threading them through JWST's crowded calendar like needles through cloth. No one expects a single event to change the story. One transit spectrum is a blur of photon noise, stellar flares, and instrumental quirks. The depth changes by tens of parts per million. The atmosphere, if it exists, might imprint a variation of just a few parts per million on top. So the strategy leans on stacking. Each new transit is aligned in time and wavelength with the others, then combined again and again, until the random noise averages down and a composite spectrum slowly emerges. By the end of tonight, you're going to understand why that composite is more like a legal case than a postcard image. The team is not looking at Proxima b in the way eyes look at planets. They are interrogating the light. At specific infrared wavelengths, water vapor should carve out deep absorption troughs. Carbon dioxide should bite hard near 4.3 and 15 microns. Methane, if it survives the star's UV, should leave its own forest of dips. In a generous Earth-thick atmosphere, those features would rise clearly above the noise floor once dozens of transits are stacked. Now, let's begin to see how the bad news appears. Suppose the stacked spectrum comes back almost perfectly flat. No water feature above the detection threshold, no CO2 band that cannot be explained as instrumental, no methane spikes that stand up even when the data are tortured from every angle. This is not nothing happened. It is a numerical boundary. From that flatness, scientists calculate upper limits. The atmosphere, if present, must be thinner than some fraction of Earth's, or depleted in certain molecules, or compressed under a heavy blanket of CO2 with almost no water at all. The pattern interrupt here is crucial. No one predicts a dramatic single frame where Proxima b flips from blue to bare. Absolutely no one anticipates a cinematic reveal. Instead, the verdict arrives as a stack of non-detections, each carefully calibrated, each narrowing the allowed space of atmospheres. The mission keeps adding transits, pushing the constraints tighter until the most optimistic versions of Proxima b quietly fall off the table, and that cumulative silence, not one disappointing observation, is what makes JWST's message so hard to ignore. That silence from Proxima b would be disappointing enough if this were just one random planet. It isn't. This was the nearby flagship, the world that checked all the easy boxes. Right distance from its star, rock roughly like Earth, orbiting the closest star in the entire solar neighborhood. If any place was going to give scientists a quick win for habitability, it was this one. Expectation, a temperate, maybe ocean-bearing planet, hugging the inner edge of a red dwarf's habitable zone. Reality, a world that, if JWST's non-detections hold, is more likely bare, blasted, and stripped. And here's why that hurts more than a simple "no life here" verdict. Proxima b was supposed to be the best-case scenario for planets around flare stars. If the best case fails, what does that say about the rest? Before we get started on the bigger picture, remember how Proxima fits into the system of nearby planets that JWST and other spacecraft are targeting. Red dwarfs dominate our galaxy. Most of the small, rocky worlds discovered so far orbit these cool, dim stars, huddled close in tight, fast orbits like Proxima b's 11-day year. That compact geometry makes them incredibly attractive for missions. More transits, deeper signals, easier to study from 4.24 light-years away. Tonight, we're going to confront the flip side of that convenience. If a planet this close to us, with such a favorable orbit for observation, still looks airless or severely eroded under the glare of its star, then many other red dwarf, habitable zone planets are probably in the same boat or worse. Constant UV and X-ray bombardment, stellar winds sweeping over them like a sandblaster, superflares detonating with energies that, over billions of years, can peel away even thick atmospheres. Proxima b is not an outlier. It is a warning label. That warning reaches all the way to the interstellar mission concepts built around this world. Breakthrough starshot and similar ideas imagined wafer-thin spacecraft pushed by lasers to a fraction of light speed, racing across the boundary between our solar system and interstellar space to capture close-up images of a potentially living planet. By the end of tonight, you're going to understand how different that target looks now. The same probes might still fly, but instead of oceans and clouds, they may be aiming at craters, rock, and a sky that never held air. There is a psychological hit here. No one expects the first neighboring Earth-mass planet to be perfect. No one predicts a guaranteed second Earth just 4.24 light-years away. But absolutely no one anticipates that our closest, most promising candidate might stand as evidence that truly Earth-like neighbors are rarer and farther than the early headlines suggested. The dream doesn't die, but it moves outward to quieter stars and more distant systems. Yet, this is not a story of despair. It's a recalibration. Every time JWST rules out another comforting atmosphere, it sharpens the search. Ruling out where life is unlikely lets scientists redirect scarce telescope time and future probes towards systems that escape this pattern of stellar violence. The question now is simple. Which nearby worlds still have a chance to break that trend, and what would it take to prove they're different? That simple question hides a quiet revolution. If Proxima b is not the nearby oasis everyone hoped for, then the real value of Webb's harsh verdict is that it tells you where not to look. Ruling out a false Earth saves decades of telescope time, mission planning, and wishful thinking that would have chased a mirage locked to a violent red dwarf. In science, a dead end is still a result. Here, it is a warning label pinned to an entire class of systems. Proxima Centauri's flares, its crushing ultraviolet output, its relentless stellar wind are not quirks. They are typical of many red dwarfs. By the end of tonight, you're going to understand that closing the door on Proxima b nudges astronomers toward quieter stars, wider orbits, and a more realistic map of where life can actually endure. That is the silver lining. JWST is not just crossing names off a list, it is reshaping the list itself. The more it peers at planets, hugging angry M-dwarfs and finds bare rock, the more pressure there is to prioritize calmer K-dwarfs and sun-like G-dwarfs for deep atmospheric characterization. Expectation: the nearest small stars would give the easiest habitable targets. Reality: their habitable zones may be dominated by sterilizing radiation, atmospheric loss, and magnetic storms. So, attention starts to drift outward, toward systems like Kepler 452, where a super-Earth orbits a G-type star in a year-long path that feels far more like home than an 11-day sprint around a flare star. Toward the future catalogues that missions like Plato in Europe and NASA's Roman Space Telescope will assemble, thousands of transiting worlds, including Earth-sized planets in temperate, slower orbits around stars that do not rage every few hours. Pattern interrupt. The most important discovery from Proxima b might not be about Proxima b at all. It is statistical. When Webb sees a stripped world here, a tenuous atmosphere there, and maybe a marginally surviving envelope around another red dwarf planet, it starts to fill in a spectrum that runs from airless cinders to fragile, possibly stable atmospheres. No one predicts a single measurement will decide habitability. The power comes from the ensemble. Tonight, we're going to treat Proxima as one data point on that curve, not a failed promise. JWST is already observing other M-dwarf systems, comparing how different stellar winds, flare rates, and magnetic fields sculpt their planets. Each null result tightens the boundary conditions. Each ambiguous hint of air tells scientists which parameters to chase, which stars deserve the next 100 hours of precious observing time. No one expects every nearby world to be friendly. Absolutely no one anticipates that the first ones checked will be the best. Proxima b's bad news folds into a larger good news story. The search is maturing. The solar neighborhood is being triaged. Step by step, Webb is teaching where the cosmic dead ends lie and where the true oases might still be waiting, just a little farther out, around calmer suns. The solar neighborhood is being triaged, so the obvious question becomes, what new eyes will we need to examine the survivors more closely? Tonight, we're going to step past Webb and into the era of telescopes that were designed from the ground up to look for fragile atmospheres, subtle hazes, and maybe even glints of oceans on worlds like Proxima b's distant cousins. The first wave is rising from the ground, On mountaintops in Chile and Hawaii, the extremely large telescope and the 30-meter telescope are being built as optical leviathans, with mirrors so wide they could swallow entire tennis courts. Designed for a 5-year commissioning, they will likely push planetary science for decades. Their raw resolving power, combined with adaptive optics that cancel out Earth's own turbulent air, will let scientists peel away a star's glare and directly study the atmospheres of nearby rocky planets, not just gas giants, worlds only a little bigger than Earth. Expectation: ground-based telescopes are for fuzzy dots and noisy spectra. Reality: these instruments will be able to take spectra of some exoplanet atmospheres line by line, molecule by molecule, measuring oxygen, carbon dioxide, and even the scattering signature of tiny aerosols lofted by alien winds. Around dim red dwarfs, an ELT-class mirror can, in principle, map temperature differences across a planet's day and night sides as it orbits, turning light curves into crude weather maps. Beyond the atmosphere, the ambitions get even larger. Concepts like Le Voir and Habex take Webb's basic idea, a cold, stable observatory parked far from Earth, and scale it up to truly audacious sizes. Now, let's begin to imagine mirrors 8 to 15 meters across in space, tuned to ultraviolet, visible, and near-infrared light. These spacecraft are not just about detecting planets, they are about directly imaging pale points of reflected starlight from Earth-like worlds around Sun-like stars and then splitting that light into spectra, detailed enough to search for biosignatures. By the end of tonight, you're going to understand why these designs feel less like telescopes and more like interstellar reconnaissance tools. With advanced coronagraphs to sculpt starlight into a dark artificial eclipse, and possibly free-flying star shades tens of meters wide, positioned tens of thousands of kilometers away, they could suppress a star's brightness by factors of 10 billion. At that level, scientists can go beyond hints of atmospheres and start probing for seasonal changes, cloud patterns, even surface ice versus ocean contrasts. For Proxima b, though, the challenge is brutal. The planet huddles so close to its star that the separation on the sky is like trying to resolve a firefly orbiting a searchlight from continents away. No one predicts an easy, direct image. But future coronagraphs tuned to red dwarf light and star shades optimized for tight inner working angles may chip away at that boundary until Proxima's glare is finally tamed. In that sense, Webb is the pathfinder. It discovered which nearby worlds are likely scorched, which might be shielded, and which deserve the colossal investment of a Le Voir-class mission. Absolutely no one anticipates that Webb is the end of the story. It is the opening chapter, telling future engineers exactly what questions the next generation of eyes in space must be built to answer. So if Webb is the opening chapter, the next question almost writes itself. Do we ever send something there? Not just another telescope in solar orbit, but real hardware, racing beyond the boundary of our own system aimed straight at Proxima b. Before we get started, imagine the scale of that ambition. Proxima is 4.24 light-years away. Even Voyager, the fastest deep space spacecraft of its era, would need tens of thousands of years. The original plan is impossible with chemical rockets. No one expects a conventional mission to make that crossing in a human lifetime. That is why concepts like breakthrough starshot feel so radical. Take a gram-scale spacecraft, attach it to an ultra-thin light sail and hit it with a phased array of ground-based lasers delivering gigawatts of power. The sail rides a man-made wind of photons pushed to perhaps 20% the speed of light. At that velocity, a tiny probe could cross interstellar space and fly past Proxima b in just 20 or 30 years. When Starshot was first proposed, the dream was almost cinematic. Tonight, we're going to picture what scientists hope to see. Oceans glinting in the red dwarf light, continents veiled by clouds, maybe even seasonal changes hinting at weather and climate. By the end of tonight, you're going to understand how strong that pull was. The closest potentially habitable planet visited not by radio waves, but by an emissary from our own solar system. Webb's new picture shatters that romance. A world probably stripped, or left with only a thin, battered atmosphere, a surface more like a fusion of Mercury and Mars than a second Earth. Yet the mission does not lose its meaning. It changes. No one predicts that a barren Proxima b would be a disappointment to planetary science. Up close, a stripped exoplanet is a Rosetta Stone for understanding how stars sculpt their planets. So, the priorities shift. Instead of zooming in on beaches that almost certainly do not exist, the probe's cameras and instruments would hunt for impact, blasted regolith, for spectral fingerprints of iron silicates and oxidized crust. Magnetometers would search for even a faint planetary magnetic field, trying to understand whether Proxima's fierce stellar wind has entirely crushed it. Particle detectors could ride the shock of each flare, mapping how high-energy protons slam into the planet's day side. Even a wisp of residual atmosphere would matter. Measuring its composition, temperature profile, and escape rate would show how far a red dwarf can push a rocky world before it fails. Now, let's begin to see Proxima not as a lost Eden, but as a laboratory for extreme space weather. Because even if Proxima b is not a second Earth, it is still the first planet beyond our solar system that we might realistically reach. A proving ground for interstellar navigation, for laser-driven sails, for communication across light years. And absolutely no one anticipates what humanity will attempt once the first pictures come back, if they come back at all. Proxima b was supposed to be comforting, a planet next door, sitting in that green habitable zone band on every infographic. But the James Webb observations pull back the curtain. The message is blunt. Distance alone doesn't save you. Before we get started redefining habitability, it helps to see how many boxes a world actually has to check. Orbital distance is only the first layer. Then come the star's temperament and flare rate, the intensity of X-ray and ultraviolet radiation, the strength of the planetary magnetic field, the ability to hang on to an atmosphere, the chemistry and thickness of that air, the presence of liquid water, and even long-term geologic activity to recycle heat and gases. Miss too many of these, and the green zone turns out to be a mirage. Proxima b is the perfect illustration. On paper, it orbits at about 0.05 astronomical units, completing a year in just 11 days, and receives a temperate amount of total energy from its star. That checks the textbook box, in the habitable zone. But the same proximity that keeps it warm also locks it under a storm. Proxima Centauri is a flare star, throwing off violent bursts of UV and X-rays that, over billions of years, can erode atmospheres, sterilize surfaces, and drive intense space weather. The planet passes the distance test and likely fails several of the others. Tonight, we're going to push past that old one-parameter picture. Earlier models treated habitable zones as simple geometry, how far from the star liquid water could exist. Now, scientists fold in flare statistics, stellar wind strength, and high-energy flux. They run atmospheric escape simulations, tracking how quickly hydrogen, oxygen, and heavier molecules are blasted away. The result is an effective, habitable zone that can shrink, shift, or even vanish entirely around the most active red dwarfs. Pattern interrupt. A planet can sit where water should be liquid and still be airless, scorched and frozen all at once. Tidal locking can trap one hemisphere in eternal day and the other in endless night. Without a magnetic field, the stellar wind rams directly into the upper atmosphere, driving off gases like a sand blaster. With too little internal heat or plate tectonics, there's no long-term thermostat, no way to stabilize climate the way Earth's carbon silicate cycle does in our own solar system. By the end of tonight, you're going to understand that this redefinition doesn't kill the dream of life. It refines it. Life might still adapt under ice deep in oceans or beneath rock on worlds that look hostile from space. But truly, Earth-like surface conditions, blue skies, stable seas, a calm magnetic cocoon are rarer than the old diagram suggested, especially around dim, violent red dwarfs like Proxima. Now, let's begin to use this new lens. The next time a headline shouts "planet in the habitable zone," you'll know to ask the harder questions. How angry is the star? How strong is the wind? And did the atmosphere survive the storm? Those harder questions come with a cost, because once Proxima b stops being a blank canvas, it stops being the perfect place to project a dream. When the planet was first discovered in 2016, the headlines were electric. Earth's nearest neighbour. Potentially habitable world just 4.24 light-years away. Artists filled the gap between a few orbital parameters and our imagination with blue oceans under a dim red sun, continents wrapped in clouds, maybe even a twilight band where day and night met in permanent sunset. For the first time, the nearest star in the system was not just a point of light, it was a destination. Tonight, we're going to sit with what it means to lose that destination. Because James Webb did not find oceans, it found a warning. The same flare star physics that made Proxima b exciting also makes it brutal, and learning that our nearest other Earth is probably barren or severely hostile lands like a small grief. The universe feels a little less generous. The map on the wall looks the same, but one of the pins just turned from green to red. This is a pattern that repeats. Mars, once imagined with canals and vegetation, is now a cold desert with a thin, leaking atmosphere. Europa, teased as an easy ocean Eden, turns out to be buried under kilometers of ice, with radiation so intense a human would last minutes on the surface. Proxima b joined that lineage. First the hope, then the data, then the adjustment. No one expects that adjustment to feel good. No one predicts that losing a fantasy world 4 light-years away will tug on real emotions here on Earth. But it does, because these planets are mirrors. They reflect a desire to know that the solar system is not a fluke, that oceans and skies and chemistry like ours are common, that the boundary between here and out there is not a hard line, but a gentle gradient. By the end of tonight, you're going to understand that this cycle is not a failure of science. It is the engine of science. Each disappointment forces sharper questions. If Proxima's wind stripped its planet, what stellar winds are gentle enough? If red dwarfs are violent, which stars cradle their worlds instead of scouring them? Every time a dream world collapses, the search narrows and the real oases come into focus. So hold both truths at once. The sadness that our nearest candidate may be a scarred, airless rock, and the awe that spacecraft and telescopes can decode that reality from across interstellar space. Before we get started on what this means for the next planets on the list, pause with that tension, because how we handle this loss will shape how we greet the next Earth-like world that appears in the glare of a distant sun. So hold that sense of loss for Proxima b for one more beat, and then flip it. What if the real headline from James Webb is not that Proxima's world is worse than hoped, but that yours is better than expected? Tonight, we're going to use Proxima's chaos as a mirror. In that mirror, the solar system does not look average. It looks suspiciously gentle, while Proxima hurls flares that can multiply its brightness in minutes and drown its planets in X-rays and ultraviolet light. The Sun, for all its storms, is a model of moderation by comparison. It pulses, it erupts, but it also gives long, quiet stretches where a fragile biosphere can breathe. No one expects that contrast to feel emotional, yet it does. Proxima b likely orbits so close that its year lasts only about 11 days, locked in a permanent day on one side and endless night on the other, with stellar wind and radiation hammering the same hemisphere again and again. Earth circles at a comfortable distance, slowly turning through day and night, wrapped in a magnetic field that catches most of the charged particles before they ever reach the atmosphere. Now, let's begin to stack those differences. Proxima's flares can spike its high-energy output hundreds of times above quiescent levels. That bombardment can strip atmospheres, break molecules, and leave bare rock. The Sun's own flares are serious, but rare and usually brief, compared to a red dwarf's relentless tantrums. Above Earth, a thick oxygen-nitrogen atmosphere and global magnetic shield turn much of that violence into auroras. Around Proxima, a planet without such defenses can lose oceans, lose air, lose time. By the end of tonight, you're going to understand why some scientists talk about the rare Earth hypothesis with renewed seriousness. Planets are common. That much the exoplanet census has made clear. There are hot Jupiters skimming their stars, super-Earths hugging tight orbits, and icy worlds drifting beyond the visible boundaries of their systems. But the exact combination that made Earth clement, a stable mid-mass star, a wide and temperate orbit, plate tectonics, a long-lived magnetic field, and just the right amount of atmosphere might be uncommon. This does not mean the galaxy is empty. It means truly Earth-like worlds may be scattered like islands in a rough ocean, farther apart than early optimism suggested. No one predicts a desert, absolutely no one anticipates a uniform garden. Instead, Proxima reminds you that many habitable zones on paper may be war zones in practice. That realization is a pattern break. The story shifts from disappointment that Proxima b is harsh to gratitude that Earth is strangely, improbably calm. And that gratitude feeds curiosity. Because if this planetary oasis is rare, the next mission, the next telescope, and the next Earth-like candidate beyond Proxima suddenly matter even more. That shift in perspective forces a harder question. If Proxima b, the poster child for nearby habitability, just fell off the pedestal, what does that do to the odds that anything living shares our immediate corner of space? Before we get started, remember how optimistic the early numbers were. Take the nearest few dozen stars, maybe out to 20 light-years. Plug in estimates that something like 1 in 5 sun-like or red dwarf stars might host a roughly Earth-sized planet in the temperate zone. On paper, there was a decent chance that at least one of those worlds was not just rocky and the right temperature, but genuinely Earth-like, with oceans, an atmosphere, and long-term stability. Expectation, a crowded neighborhood of quiet, blue marbles. Reality, as JWST sharpens the view, is drifting in a different direction. Tonight, we're going to treat Proxima b as a data point, not a disappointment. When a world this close in the nominal habitable zone shows signatures of atmospheric stripping, brutal flares, and a relentless stellar wind, it does more than doom one planet. It pushes scientists to rewrite the odds for every red dwarf in the catalogue. Those compact, cool stars were supposed to be habitability engines, long-lived, efficient, everywhere. Now each one looks more like a potential executioner of atmospheres. By the end of tonight, you're going to understand why removing Proxima b from the likely column hurts the statistics. Inside a radius of 10 to 20 light-years, most of the known small planets hugging habitable zones belong to red dwarfs. If strong magnetic fields and violent flares are common, then many of those orbits are not gentle shoreline properties. They are erosion zones. The probability that one of those nearby systems hosts a truly Earth-like surface, liquid water, thick air, mild radiation, drops, not to zero, but from plausible to surprisingly hard to justify. Other candidates remain. Planets around calmer stars like Tau Ceti, compact systems around cooler objects such as Teegarden's star, worlds not yet discovered by this generation of spacecraft and surveys. But after Proxima, no one expects a simple box check of radius, mass, and insolation to be enough. No one predicts that in the habitable zone will automatically mean habitable. Each new target now faces a higher bar. Magnetic environment, flare history, atmospheric retention, all interrogated with the intensity once reserved for only the most exotic planets. Of course, life does not have to play by Earth's rules. Subsurface oceans on icy moons, rogue planets with buried seas warmed by radioactive decay, exotic chemistries in methane lakes, or supercritical atmospheres. The galaxy could be full of these hidden biomes, but they are harder to detect, less likely to paint the sky with oxygen or methane signatures that JWST can see from across the dark. So the paradox emerges. The Milky Way may still be rich in life, yet the volume within a few light-years may be lonelier than hoped. And if the closest promising world just failed the test, the next question is brutal and irresistible. Which nearby planet gets put under the microscope next? And what happens if that one fails too? So when the question lands, who gets put under the microscope next, the unsettling answer is that the target keeps moving, because the science keeps moving. Proxima b was only discovered in 2016. Before that, the closest potentially habitable world in the entire solar neighborhood was invisible, buried in noise. The entire narrative arc of this planet, from thrilling announcement to grim James Webb constraints, has unfolded in less than a decade. That is an eye blink in scientific time. Tonight, we're going to stand inside that eye blink and watch it stretch. In 2016, the headline was simple: Earth mass planet, temperate orbit, right next door. By 2019, there were models of oceans under dim red skies, slow winds, and maybe a twilight band where liquid water could persist. By the time JWST came online, those early hopes had hardened into specific predictions: how much infrared glow a thick atmosphere should produce, what kind of thermal phase curve a living world might display. Then the data started arriving, not just from Proxima, but from TRAPPIST-1, from other red dwarf systems, from X-ray and ultraviolet telescopes that measure how violent these stars really are. Each new paper nudged the picture. One simulation would say under a dense, magnetically shielded atmosphere, Proxima b could endure. Another would show that a single superflare could strip that same atmosphere over geologic timescales. Prediction versus observation over and over, with JWST quietly tipping the scales. Here is the pattern interrupt. This is not a courtroom delivering a final verdict on Proxima b. It is a live feed from an ongoing investigation. Some of the results discussed are still under active debate. Different teams extract slightly different signals from the same spectra. Some argue the thermal contrast is compatible with a thin, battered atmosphere. Others argue it screams bare rock. No one expects consensus this early. No one predicts that a few years of data will settle the fate of an entire class of worlds. By the end of tonight, you're going to understand that JWST's bad news is not the end of the story. It is the beginning of a sharper one. Future JWST cycles will revisit Proxima, catch it in different flare states, probe different wavelengths. Next-generation missions, the extremely large telescope on the ground, future space observatories designed to block out stellar glare and image planets directly, could either confirm that Proxima b is airless or reveal faint, stubborn traces of an atmosphere hanging on at the edge of survival. So, this is a snapshot, not a monument. The closest exoplanet will remain a key test case for how stellar wind, magnetic fields, and atmosphere interact around red dwarfs. As new spectra drop and new models rise to meet them, the boundary between habitable zone and actually habitable will keep shifting. Now, let's begin to follow that shift outward to the next nearby worlds lining up in James Webb sites. We started with one world, Proxima b, as a cliffhanger, a maybe ocean, maybe desert, maybe dead rock. But if the closest habitable zone planet is probably thin-aired or stripped, you have to ask a bigger question. Is Proxima b unlucky, or is it normal? Tonight, we're going to upgrade the mental model. From single dramatic planets to entire populations, from is Proxima b habitable to what happens to small rocky planets around stars like this over and over again. That shift is where the real power of James Webb and the new generation of surveys appears. The old habit in exoplanet science is easy to understand. A new world is discovered. It gets a press conference, an artist's impression, a nickname. Kepler 452b, Trappist 1e, Proxima b, each one treated like a main character. But the mission architects and the scientists driving these spacecraft are quietly doing something else. They are building statistics. By the end of tonight, you're going to understand why that matters more than any single disappointment. JWST is not just staring at Proxima. It is sampling dozens of small, close-in planets, while other missions and ground-based telescopes extend the census to hundreds and soon thousands of rocky worlds, around cool red dwarfs, around sun-like stars, around everything in between. Every time a planet transits its star, a sliver of starlight filters through whatever atmosphere it has left. JWST reads that sliver. Sometimes it finds thick hydrogen envelopes, sometimes dense metal-rich atmospheres, and sometimes almost nothing. A flat line that screams bare rock. When those flat lines keep showing up around active red dwarfs, the pattern becomes hard to ignore. Proxima b is no longer a lonely verdict. It joins a growing family of worlds, hugging tiny, violent suns, where flares, X-rays, and relentless stellar wind push at the atmospheric boundary for billions of years. TRAPPIST-1's inner planets, GJ 1252b, several ultra-short period worlds whose spectra hint at scorched surfaces and vanishing air. No one predicts each case in detail, but as a population they start to rhyme. Now, let's begin to see how that changes the search for life. When scientists compare ensembles instead of one-off curiosities, they can separate what is typical from what is exceptional. Typical might be active red dwarfs strip many close-in rocky planets. Exceptional might be a quiet star with a magnetic field and wind gentle enough to let a thin, temperate atmosphere survive. The more planets are added to the catalogue, the sharper that contrast becomes. Proxima B's grim outlook stops being a tragedy and becomes a data point, a warning label on an entire class of systems. And that, paradoxically, is hopeful, because it tells you where not to look, so you can focus on the rare configurations that might truly echo Earth. In other words, individual worlds can disappoint, but the pattern they reveal is gold. The mission now is to read that pattern correctly. The mission now is to read that pattern correctly. And Proxima b sits right on one of the most important lines that pattern is drawing, the true edge of our habitable neighborhood. Before we get started, think back to another edge that turned out to be a mirage. For decades, textbooks showed the solar system ending at a neat circle where the sun's influence just stopped, a clean frontier. Then the Voyager spacecraft kept going. They discovered that the edge was not a line at all, but a sprawling, turbulent region where the solar wind is slowly strangled by the interstellar medium. Designed models said the termination shock should be near 90 astronomical units, a tidy distance. Reality pushed it out and warped it. The boundary was farther than scientists predicted. The shape was distorted. The magnetic field twisted in ways absolutely no one anticipates on paper. The edge became a messy, layered transition, not a fence. Tonight, we're going to use that same mental upgrade on habitability. The old picture was simple. Draw a circle around a star where liquid water could exist on a rocky planet and call that the habitable zone. Find the nearest Earth-sized world in that ring and declare it the frontier of our habitable neighborhood. Elegant, clean, wrong. Because Proxima b shows that the real boundary is not just about distance, it is about survival. Around a calm, sun-like star, the habitable zone is a relatively gentle band. Around a flare-star red dwarf, it can be a shooting gallery. Proxima's intense ultraviolet and X-ray radiation, its violent stellar wind, and its frequent flares mean that a planet can sit at the right temperature and still lose its atmosphere, molecule by molecule, over billions of years. By the end of tonight, you're going to understand why that makes Proxima b feel less like a neighbor and more like a warning sign hammered into the ground at the edge of town. On paper, it is the closest potentially habitable planet in the entire system of nearby stars. In practice, every new observation from James Webb pushes it a little further beyond the line of true habitability. So where does that line really fall? If Proxima b is just outside, maybe the real edge of our habitable neighborhood lies farther out around quieter stars, orange K-dwarfs with softer stellar winds, or even some red dwarfs that calmed down early, whose planets still hold on to thick, protective atmospheres. No one predicts that the first Earth 2.0 will be the closest candidate. Space has never been that generous. Now, let's begin to treat this not as bad news, but as calibration. Voyager turned the edge of the solar system from a cartoon into a complex, living structure. Proxima b is doing the same for habitability, forcing a redraw of where home-like worlds can actually exist. The humbling part is that the universe keeps overruling the first draft. The exciting part is what that implies about the worlds we have not yet seen, because if the nearest candidate is already beyond the boundary, what does that say about the planets just beyond our current reach? So at this point, You are not looking at Proxima b the way most people still do. The headline version is Earth's nearest twin in the habitable zone. The version you now carry in your head is a stripped, irradiated world clinging to a violent red dwarf, where the word habitable has to fight for every letter. Tonight, we're going to make that transformation explicit, because what you now understand is not just a list of new facts. It is a new way of reading the entire sky. First, you can see through the old hype. Proxima b hugs its star at about 5% of Earth's distance from the Sun. On paper, that keeps liquid water possible. In reality, you now know that frequent flares, superflares, and a relentless storm of UV, X-rays, and charged particles can sandblast a planet's atmosphere until only rock and regret remain. No one expects a gentle climate under that kind of solar wind. By the end of tonight, you're going to understand that when scientists say we didn't detect a thick atmosphere, that sentence is loaded. You now know how transit spectroscopy lets a spacecraft like JWST watch starlight filter through a planet's limb, searching for the faint fingerprints of gases that have survived. You know that when those fingerprints are missing, one explanation is atmospheric escape, gas heated, ionized, and literally driven off the planet by the star's radiation and wind. You can also picture thermal phase curves now, not as jargon, but as a moving map of day-night, contrast on a world you will never visit. A small temperature difference hints at air, moving heat around. A brutal day, night split whispers bare rock, no blanket. That is a conceptual upgrade most people never get. And that classical habitable zone diagram, one neat green ring around a quiet sun, you've seen why that is only a first draft. Around red dwarfs, the same orbit that keeps water from freezing can lock a planet into tidal day and night, expose it to superflares, and push it across a very different boundary, the line between sheltered and shredded. Here's the pattern interrupt. This is no longer just about Proxima b. You now grasp that its bad news is a data point in a much larger mission. Red dwarfs are the most common stars in the galaxy. If their habitable planets are routinely stripped, that reshapes the odds for nearby life and pushes truly Earth-like worlds farther out, around rarer, calmer stars. Before we get started on those more distant targets, recognize what this gives you. You are no longer just a passenger hearing that a new Earth-like planet has been discovered. You can ask, what is the star like? How violent is its magnetic field? Is there atmospheric evidence or just an orbit in the right temperature band? Is the climate stable for billions of years or living on borrowed time? That critical lens is a superpower. It means that when the next wave of exoplanet headlines hits, you will not be surprised when theory and reality clash. You will be ready to follow the scientists to the worlds beyond Proxima and to understand what their silence or their signals actually mean. That critical lens is a superpower. It means that when the next wave of exoplanet headlines hits, you will not be surprised when theory and reality clash. You will be ready to follow the scientists to the worlds beyond Proxima and to understand what their silence or their signals actually mean. Because Proxima b, our nearest potentially Earth-sized neighbour, now looks less like a welcoming shore and more like a warning sign. Designed in our imagination as a quiet, dim sun sanctuary with oceans and clouds, it is turning out to be a place where stellar wind, radiation and time have probably carved away much of what life would need. The universe, it seems, does not hand out second Earths cheaply. That contrast matters. Expectation versus reality. A temperate orbit on paper versus an 11-day year spent hugging a flare star that lashes its planets with X-rays and ultraviolet light. Proxima b orbits in the so-called habitable zone. But JWST's view suggests a much harsher boundary, the line between worlds that can hold an atmosphere for billions of years and worlds that lose that shield grain by grain to the star. Now, let's begin to zoom out. Proxima is one star, one red dwarf in a galaxy of hundreds of billions of stars. Even if many red dwarf systems are this hostile, even if tidal locking and stellar storms strip planet after planet, that still leaves unimaginable room for quieter suns, wider orbits, and more forgiving environments. Tonight, we're going to hold two ideas at once, that our nearest candidate may be bleak, and that the larger cosmic landscape is still wide open. By the end of tonight, you're going to understand why every no is not a defeat, but a calibration. No one predicts that the first nearby exoplanet in the spotlight will give perfect conditions. No one expects the early targets to match the hopeful headlines. Each disappointment sharpens the search, refines the climate models, and tells mission planners which planets deserve the next precious pointing of a future spacecraft. Imagine a future where thousands of nearby planetary systems are mapped in exquisite detail, where the catalogue is not a handful of famous names, but a true atlas of the local galaxy. In that atlas, Proxima b will be there not as the lost Earth 2.0, but as one of the first hard-won data points, a marker that says, here is what a close-in world around an active red dwarf really looks like. The emotional truth is simple and unsettling. The cosmos is harsher and more complex than hoped, yet the fact that a telescope orbiting the Sun can read the scars of stellar violence on a world 4.24 light-years away is its own kind of miracle. Absolutely no one anticipates that level of insight a century ago. From this distance, to have discovered so much about a single rocky planet is already a profound achievement, and it is only the beginning. From this distance, to have discovered so much about a single rocky planet is already a profound achievement, and it is only the beginning. Because there is a pattern here. Voyager showed that the edge of the solar system was not where textbooks placed it. James Webb is now doing the same thing to the edge of our imagined habitable neighborhood. Designed expectations collide with hard reality. The habitable zone diagram in a classroom looks clean, a neat green band around a quiet star. Proxima b sat right in that band. It was the poster child for a nearby Earth 2.0. Then the data arrived. The flares, the radiation, the likely stripped or suffocated atmosphere. The boundary was harsher than every scientist hoped, and the path to a truly gentle world moved farther away. Tonight, we're going to connect those two journeys. Voyager's twin spacecraft pushed through the solar wind, crossed the termination shock, and found a heliopause far beyond what models predicted. Webb, locked in its halo orbit around the Sun-Earth system, stares across 4.24 light-years and finds another kind of shock. A planet in the right place on paper, in the wrong environment in practice. By the end of tonight, you're going to understand that both discoveries are chapters of the same mission. The arc of this episode runs from optimism to nuance. First came the hope, a rocky world around the closest star, bathed in just enough light to keep water liquid. Then came the sobering measurements, flare star violence, extreme ultraviolet and X-ray flux, stellar wind that can sandblast an atmosphere for billions of years. Finally comes the deeper understanding, habitability is not a single distance. It is a negotiation between star and planet, between energy and shelter, between time and survival. Yet the emotional core does not dim. A species that can throw two spacecraft out of the solar system and aim a telescope with nanometer precision at a dim red dwarf is a species obsessed with one question: are we alone? Every radioisotope generator on Voyager, every gold-coated mirror on Webb, every line of code that teases meaning out of a few lost photons exists to push that question a little closer to an answer. So Proxima b is not a dead end. It is a milestone on a growing map. Its bad news tells scientists where not to look, which stars to treat with suspicion, how stellar wind and radiation carve away the fragile envelopes that life depends on. Each disappointment sharpens the search, steering future spacecraft toward quieter stars, thicker atmospheres, more promising planets beyond our current reach. Before we get started on that final map, remember what this really is: a shared expedition. Watching, questioning, staying engaged with each new result is part of the same long mission that began with Voyager's launch and continues with Webb's warning. Because if the nearest Earth turns out hostile, the obvious question is, what does that say about the worlds we have not yet seen? So if you're still here, after more than 2 hours in orbit around one hostile little world, that says something. Out of millions of people scrolling past, you're in the tiny fraction that genuinely wants to understand where we fit in this vast solar neighborhood and beyond. That curiosity matters. It is not just passive watching, it is part of the mission. When you like this video, subscribe to the channel and share it with someone who still thinks habitable zone automatically means definitely habitable. You are pushing a more accurate, more awe-inspiring picture of reality out into the network. Expectation: friendly Earth 2.0s lined up around every red dwarf. Reality: a violent Proxima, a stripped or battered Proxima b, and a universe that is far more complex and far more interesting than the brochure. There is a direct line from your engagement to what can be explored next. Long-form deep dives like this take time, data, and focus. They only happen when the signal is strong enough that platforms, algorithms, and even scientists can see that people actually care about careful, slow, 2-hour examinations of a single exoplanet's fate. No one expects that to be a winning formula. No one predicts that a detailed breakdown of stellar wind, atmosphere loss, and spectral lines will hold attention. Yet here you are. So, if this journey through Proxima's flare-lit system has been worth your time, press like. Subscribe so you do not miss the next chapter. Share it with the person in your life who still imagines the universe as a quiet grid of stable, welcoming planets, and invite them into the harsher, truer, more beautiful version that scientists have actually discovered. Because tonight, we're going to treat this as a beginning, not an ending. The next episodes will follow the same trail outward to the TRAPPIST-1 system, where 7 worlds crowd close to a dim star under relentless radiation, to the next generation of telescopes that will try to read weather patterns and oceans from a single pixel of light, to the first true Earth analogues that might show oxygen, water vapor, and seasons in their spectra. By the end of tonight, you're going to understand that Proxima b is not a disappointment. It is a calibration point. Here is a concrete next step. When this ends, jump to the deep dive on James Webb's other discoveries, or to the long Voyager episode tracing those 2 spacecraft from the inner planets to the edge of the heliosphere. One shows how a modern observatory is rewriting the catalogue of distant worlds. The other shows how a pair of 1970s machines crossed the boundary into interstellar space and measured the wind between the stars. Now, let's begin the larger search. Somewhere out there, around some distant star, there may be a world that really is another Earth. Until that first true twin is found, Proxima b will stand as a quiet warning in the dark, a reminder of how hard the search will be and how important it is that you stay on it. Now, let's begin somewhere stranger. Imagine Proxima b answering back across 4.24 light-years, not as a failed Earth, as a survivor. "You call this region my star's habitable zone," the planet would say, "but you forget what it is like to live pressed against a red dwarf skin. From the first moment the molten crust cooled, the sky above was not gentle blue. It was a furnace. Flares carved scars into my air. Ultraviolet light unmade the molecules your scientists hope for." In this voice, Proxima b remembers an atmosphere that did not last. Hydrogen leaking first, then heavier gases torn away in slow, invisible rivers. The stellar wind thick with charged particles, ramming into its magnetic boundary, if it ever had one strong enough to matter, until the shield thinned, then failed. Oceans that models once painted across its surface never had time to settle. Steam, then loss. Clouds, then vacuum. A world that cooled from magma, not into seas and continents, but into the bare rock James Webb now sees outlined in brutal clarity. "Tonight, we're going to pretend you can hear that," the narration continues, because the story it tells is exactly what the mission is uncovering. Proxima b would speak of flares that outshine its tiny sun for minutes at a time, of X-rays and extreme ultraviolet light pounding the same hemisphere over and over, because tidal locking means one face almost always watches the star. Day is punishment, night is deep freeze. "You looked at me and projected oceans," the planet would whisper. "You imagined clouds, perhaps even cities, glittering along a twilight band. You saw a mirror for your solar system, a nearby refuge just one good spacecraft away. But what you discovered instead is how fragile that dream is. You wanted another Earth. What you got was a lesson. By the end of tonight, you're going to understand why that lesson matters. Every stripped world like this is not just a disappointment, it is a data point." Each bare, irradiated rock tied to a red dwarf helps scientists refine the equation that asks how many planets go beyond simple habitability on paper and actually keep air, water, and time long enough for life. Prediction versus observation, written in stone and missing atmospheres. No one expects the nearest potentially habitable planet to be a warning label. The voice of Proxima b might say, no one predicts that the closest path outward from your sun leads first through loss. Yet that is what this system offers, a caution at the very beginning of the map. And still, it is not only grim. Proxima b stands like a signpost at the edge of the local neighborhood. It points past itself, past its violent red sun, into deeper space where other stars burn calmer and wider. Somewhere beyond this harsh boundary there may be planets that held on, worlds that rode out their stellar wind and kept their skies. "Look at me," the planet would say, "and then look further." Somewhere out there, past the familiar bright patterns of the night sky, Proxima Centauri drifts as just another faint point in a crowded starfield. On screen, the camera moves slowly, almost hesitating across dense curtains of stars and hazy rivers of distant galaxies. No rush, no drama, just the quiet geometry of the cosmos unfolding in front of you. A tiny label appears near the edge of the frame, Proxima Centauri. Nothing flashes, nothing zooms, the text just hangs there as the star slides past, reminding you that the entire story of this mission, this planet, this warning, is tied to a dot you would never notice on your own. As the view glides on, the names begin. The engineers who built a telescope that can read the fingerprints of alien atmospheres, the scientists who wrestled with noise and glare and solar wind to pull a signal out of the dark, the mission teams who keep this spacecraft steady and cold 1 million miles from Earth. Without them, Proxima b is not a world. It is just a number in a catalogue. The frame drifts over a spiral galaxy, its arms thin and ghostly. Somewhere in those swirls, planets circle other suns, some calm, some violent, some already lost. The narration stays spare. Thank you to the observatory staff on the ground, to the programmers and analysts who turned raw photons into meaning, to the broader community that spent decades arguing for a telescope like this, long before a mirror ever saw space, designed to map the first galaxies and the earliest light in the universe. Tonight, we're going to remember that it also turned back toward our own neighborhood and found a different kind of edge. No one expects a single observation to rewrite the odds of life around red dwarf stars. No one predicts that one harsh result will echo this loudly. Yet absolutely no one anticipates how powerful it feels to diagnose the fate of a planet that no human will touch for centuries. The camera finally finds another small label, Proxima Centauri b. It is barely off-center, drifting slowly, almost lost against the background. By the end of tonight, you're going to understand that this is a triumph as much as it is a warning. From 4.24 light-years away, across a boundary of vacuum and time, a civilization that still struggles to reach its own outer planets has already discovered how neighboring worlds live and die. When the video ends, let the screen go dark and stay with that distance. Sit in the silence for a moment and feel how close that alien neighbor is in the scale of the galaxy, and how unreachable it remains in the scale of a human life. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together.